Alright, let's go do the thing. Alright. No, not a host. Okay. Welcome. Hello, welcome to stream. Today we do the streaming again. Alright. Spreading around those links. Oops. This is a new setup, by the way. Oops. All right. Let's see here. All right, let's go. Welcome, single viewer. All right, let's see. All right, what are we doing today? We are doing batterifying, improving the 4D render pipeline is what we're doing. For now. All right, boink. Let's go. Okay. All right, internet connection is great. Sounds good. All right, I've been told before that the font size was too small, so is this fine? Is this better? What I want to know is this better by any means? Is this good enough? All right. Welcome, welcome, welcome. Welcome to stream. Today we do a kind of a good, better rendering pipeline that we did last time. Last time we did a box. Last time we did a 4D box, I mean. And the 4D box looked like, sorry. What did the 4D box look like? Coming in a moment. Alright, terminal, wink. 4D box looks like that. Oops. Shit. Off to a good start. Alright. Alright, this is what the 4D box looks like. Well, it didn't look like that, but now it does. I went through... Oops. That's kind of ugly. Okay, right. Better. Alright, much better. So this is what our 4D box looks like now. So, last time we did basically this, is all. We did a triangle intersector. tetrahedron intersector, I mean. Last time we wrote this box class, we improved on it. We generated the 4D geometry from this 3D geometry over here. What else did we do? Yeah, that's mostly it. We set up the render pipeline, and we did some 4D math with the matrix 5 class that I added. If I meant. We intersected them tetras. That's for sure. Some tetras got intersected over here. Okay, so we took all the tetrahedra that resulted from the extrusion of the 3D geometry into 4D. That gives us a bunch of hang on. That was using the geometry 4D class, yeah, like this. Take all the 3D vertices, add a couple coordinates, and then make tetrahedra out of them. That's what we did. What else did we do? Couple of OpenGL shit. Did some 4D rotation using the matrix 5 API that I wrote, of course. Yeah, last time we only did simple like push vertices into triangles and render everything. I took a bit of time off camera to add some functionality. Basically, all I did was change it so that all the resulting triangles from the intersection of the tetrahedra, they were pushed vertex per vertex. So now it's not anymore an index array. It's actual like draw arrays. I feed the vertices. I feed it based on vertices instead of triangles, because now I want to have a 3D normal from the triangles. Here you can see when I do a push triangle, what I mean is push 3 vertices and then push the normal 3 times, just in order to have a simple, well, kind of ad hoc normal vectors. That works. It works because right now we have this, as I said. It's pretty neat. It's got shading. It allowed me to do a little bit of shading, and this is actually what it's a more accurate representation of what a 4D box is supposed to look like. Well, if it's supposed to look like anything, because 4D extra, of course. So that's what we have. I did simple, like, stupid shading. Basically, all it is simply just taking your normal like run-of-the-mill Lambert shading. Basically, I'm using double-sided triangles because we yet have to define what orientation means in 4D, but we're gonna come to that today actually, if everything goes well. So yeah, I'm using this basically, just plain red, and if the face is facing straight to the camera, then it's maximal lighting, and then if it's looking to the side, it gets slightly more shaded, etc., etc. Okay, so nothing too extraordinary going on here for now, except that we are of course displaying an actual 4D box, which is pretty cool, if you ask me. Alright, so today what we want to do is we want to basically ditch everything that is 3D and turn it into 4D. What I mean by that is we want, well, except for the geometry, because it's easier. So we're gonna look at one issue of doing things this way, because when you extrude 3D geometry like that, you have a problem, which we're gonna talk about in a minute. So plan for today is, as I said, improving the 4D render pipeline. So basically what that means is get rid of everything that is 3D, and instead of calculating it like stupidly on render like that, for example the normal vectors of all the triangles, it's very inefficient and also doesn't allow for correct orientation and backface culling, because I don't know which way the triangles are supposed to be facing. Because I'm calculating the triangles based off 4D tetrahedra, and I still don't know, and still I'm not sure on what looking in directions means in 4D, right? So I have to calculate, first of all, we're going to calculate the 4D cross product between 3 vectors. Ooh, new mathematics up in here. I don't believe this has been done before, although you could easily, well, easily, what's easy and what's not easy, but you could, without too much trouble, if you know your math, you can infer a cross product for any dimensions, as I've talked about before, in the previous stream, in fact. So I did just that, and I have in my vector 4 class a 4D cross product, which I called very aptly cross product 4D. Takes 3 vectors, gives us a 4th vector that is orthogonal, blah 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 blah, you know the drill. It's the exact same as the 3D cross product, but in 4D. And it has the same properties. It's also telling us in which quote-unquote direction the tetrahedron is looking. Again, define direction in 4D, but that's also something I'm not familiar with, so we're going to discuss it together and see how that goes. At the most, good morning to you. Good morning. Oh, the lecture has already started. Yeah, we just started. We started 5 minutes ago. Are drinks allowed? Yes. You might even say that drinks are recommended. No, don't. I mean, you do you. You do you. Drinks allowed, yeah? Sure. And the lecture has already started. It's not a lecture. If anything, this should not be a lecture, because please feel free to interrupt me at any time and ask questions. And if you think you're being boring, chances are you're not. But if you are, I will tell you so. I will be relentless. No, I'm kidding. Please ask away anything you have in mind, because this is complicated. How do I pronounce your name if I want to? You can call me Matt or Matrif. And if you want to go the French route, as I am, then you will have to say something along the lines of Matt refait ton pièce, in which case, good fucking luck. Yeah, Matt or Matrif will have to do. Will do, I mean. If you are amongst the brave ones, then you can go with the full name. Your name is awesome, thank you. I also think it's pretty cool. Your name is not bad, I would say, at the most. Alright, so yeah, as I said, 4D cross product. But then we have to actually understand, can I call you French person? Well, I guess. As long as there is nobody, as long as I'm the only French person in chat, then yeah, because then it's not ambiguous. I'm fine with being called French person. Oh hey French person, what you doing? Doing math again? Yeah, I am in fact. Should not only have taken Latin, but also French. I didn't take Latin. I didn't even take French. Yeah, of course. Latin is... Again, you do you, but Latin? Hey, you know who else took Latin? Nobody. They're only dead. They're all dead. Haven't seen the HX files yet. This language is called Hex. Like this. In the terminal. Oops. It's called Hex. And basically it's a cross-platform language. The language is defined to run on other languages. Okay, it was this minus version, yeah. So this language is object-oriented, with pattern matching, some aspects of functional programming. The Hex language is used to, as you can see here, compile to many other languages, and it does so very, very well, in fact. Is that Flash develop or Hex develop? That's Notepad++. That is Notepad++, because I don't like IDEs getting all up in my business when I do like auto-completion or something like that, because I like to write out everything myself. I want to go the stupid, boring route of having to... Yeah, I don't like auto-completion. Yeah, I don't. Because it's getting... It has a history of getting in my way, and I very much don't like that. It's annoying. But yeah, I have been told, although, that Hex develop is the way to go. Flash develop is getting kinda off purpose, and Hex develop is being worked on in order to be like the go-to Hex IDE. So I depend on it in my life because of my spastic fingers not being able to type. Yeah. Well, yeah, I understand that. it's not a very popular opinion that I have. By any means, not asking anybody to follow that. But that's how I roll. Okay, well, what will you be doing? What will we be doing today? Today we will take the 3D geometry, take our generated 4D geometry that we did last time. It's 4D. In case anyone hasn't seen it yet, this is what we did last time. We have a working 4D box. It should be coming. It's taking a while for OBS to pick it up because it's an OpenGL surface, and I have to render it to capture it. I mean, as a game window. So yeah, this is what we have. This is our little 4D scene. This is a 4D box being subjected to 3 consecutive rotations. This I'm gonna show you in code what that looks like. So basically, last time what we did is have UMAT, which is the 4D model matrix. So as such, it's a 5x5 matrix, of course. Basically, just create an identity matrix, scale it so that the box has the dimensions that we gave it, and then I apply 3 rotations. So of course, that's like pretty fucking not the way to do it, but it's just a test. Again, it's not definitive code by any means. Rotation around XY, XZ, and YW. Various, like I used various timers with like minus or not just to spice it up, and that's what it gives. VS Code plugins for hacks have become pretty good. Yeah, the one thing to notice about hacks, I think it is fun to use. Oh yeah, it's very fun. I've been toyed around with Hacksflix and was pleasantly surprised. It is not much slower than using maybe GameMaker. The language feels more mature. Yeah, that's a good thing about hacks. Like, hacks is built in order to be compiled to different languages, so as such, many features of the different languages are target specific, but are in fact included in the language. So that's really cool. And it makes it so that generated code is, in most cases, exactly as fast as handwritten code. So that's like a win-win. Are you projecting the 4D element into 3D space? Arguably yes, but strictly speaking, no. When you think about projection, you mostly hear, oh, take a 4D object and quote unquote put it in 3D. So in that case, kinda yeah, but also no, because what we are doing is a technique I call hyperplane slicing. Basically, hyperplane slicing, how that works is we have this class over here, which I called intersector. Basically, what this is a 3D space. It's a 3D space sitting in 4D space. Basically, it's a part of 4D space, and we are using this as a field of view, a 3D field of view for our camera, which is implicit here. I didn't write a camera class, but I'll come eventually. This 3D space is what is called a sub-vector field, or vector subfield. I'm not sure. Vector subspace, something like that. And basically, yeah, it's exactly what you think. It's the equivalent of a plane in 3D, but it's a 3D plane, so you call it a hyperplane, basically. It's got a normal vector. Again, you can see here hello? Hyperplane? Yeah, you can see here the Cartesian equation. AX plus BY plus CZ plus DW plus E equals 0. So that's the Cartesian equation for the hyperplane. Exactly the same as a line in 2D and exactly the same as a plane in 3D. It's just a hyperplane. And here in my case, because I don't have an anchor, I just use 0. So E is 0. And the equation just becomes like V dot product with the normal of the vector. So it's linear algebra stuff. Sorry, you are right. I actually meant development speed, executing speed. I would trust hacks to be far better in executing speed. Yeah. Oh yeah, it's actually very fast to use also as a language and to write. It's close to ActionScript and Java in this regard. My brain hurts from exposition to 4D space. Everybody's brain hurts. It's fine. Don't you worry. Yeah, that is what I mean. Mathematical projection of 4D vectors to a 3D plane and then onto the normal projection. And then you are wrong again. Because I don't do projection, I do slicing. Projection will be have a linear algebra type projector, which is a linear function, but we don't have that actually. This 4D plane, this hyperplane, is used to slice tetrahedra as hinted at by this function over here. And what this does is basically just calculate the intersection between the plane and the tetrahedra. This is why we use tetrahedra in place of triangles, where we would normally do in 3D engines. But the reason for that is very simple. It's because in the 3D engine, objects are 3D, and we can define them using their surface, because 3D objects have a closed surface that defines volume. So if you just define the surface, it's easier than defining the volume. And we do that using a tiling, using triangles. And well, in 4D, the same thing. A 4D object is a 4D volume. We call it a hypervolume. And this hypervolume is defined by an enclosing 3 volume. And this 3 volume can be expressed using tetrahedra, because it's like tetrahedra are the 3D equivalent of triangles. And as such, they are easy to use compared to other shapes. And that's what you're doing. So yeah, it's not projection, it's intersection between a 3D space and tetrahedra. And said intersection gives triangles, and this is basically an array of intersections. And when you return that, you catch it in the box class here. Intersect, this gives a function, an array. And then on every array, you do a change of basis to express all the intersections in the base of the intersector, which is again the 3D space. And when that's done, you basically push triangles depending on the number of vertices of the intersection. The intersection can have 0, 1, 2, 3, or 4 points. 0, 1, and 2 we ignore, because it's just like either the tetrahedron is not in the plane, or only one vertex or one edge, and that we don't care about. If it's 3, then it's a single triangle, so we push it. And if it's 4, it's either a quad, in which case we stop here, or a tetrahedron, and in which case it's actually 4 triangles, so we push 2 more. And this gives a regular good old 3D scene that we then feed to OpenGL, and it draws, and it's fine. There are not many hack streamers, but I'm actually very pleased to get to know you as a streamer. Oh, well, thank you. How about creating a paid hacks online course, maybe on Pro's site or on Udemy? You seem to know what you're doing. Well, I've not at all considered that. And first of all, wow, thank you. And yeah, I like to know what I'm doing, but I could have used any language. Like, it's not so much language specific as very abstract math, and I have a very heavy math background, and I'm very interested in what I'm doing anyway. So yeah, I have not at all considered creating a paid hacks online course. I don't think I know enough. And even if I did, I'm actually currently attending engineering school. This is my 2nd year. I'm a 20 years old French student. For all you stalker in the chat, please don't. And yeah, I'm sorry, but I clearly don't have the time. I maybe consider it in the future, who knows. But if you're looking for help on the hacks language, there is a hacks Flixel Discord, which is actually which has just turned into a hacks Discord over the time. I mean, so you can search online for hacks Flixel Discord. You can join that like freely, and also the hacks community actually started a discourse-based community. See if I can't find it again. Community.hacks.org. Yeah, I'll just post that in chat. Hacks is very similar to TypeScript. Yes, there are many automated converters from and to hacks and TypeScript. And actually, 3.js, French math education seems a lot better than German math education. I have a degree in computer science and computer laws with this stuff. Yeah, well, thing is, I did not do I did not just do engineering, right? In France, you have this thing called CPGE, which are basically prep school, but like public prep school. And it's a 2 very intensive year when you do a lot of math and physics in order to get to the higher engineering schools. And that's what I did. And also, I'm very passionate about math and physics anyway, so I research this a lot in my free time. So don't by any means, like, if you are lost, feel free to ask any question that you have while I move on. Okay, so yeah, from the last time we only had a simply flat shaded box of boringness. And so what I added, I just added a couple of things. Basically, I removed the fact that we were using a triangles array. No triangles array anymore. And last time we were using draw elements over here, gl.draw elements, in order to not have to reuse vertices. In order to reuse vertices, I removed that because the same vertices need different normals because of the fact that we are drawing tetrahedra. And as such, tetrahedra have non-continuous gradient, and because of that, they have non-continuous normal vectors. So we need to have, we can't just have one normal vector per vertex. We actually have to go at it on a per triangle basis. So that's why my push triangle function recalculates the normal product every time. This is what we're going to try and improve. Thank you very much for streaming hacks. Good night, sleep well, have a pleasant evening. Thank you. I'm not planning on sleeping anytime soon, though. I had linear algebra in my first semester of computer science, and I'm German. Shaders are killing my brain, though. Well, shaders are the epitome of linear algebra. You are doing linear algebra all day, every day on shaders, like this, for example. This right here, dot product between a normal vector and the direction, the position, is shorthand for the camera is the light and the triangles are double-sided. This is what this line means. Because we don't care about the sign because of the absolute value, and we use, as the direction from pixel to light, we only use the position of the pixel. So it points at the camera, basically. Alright, moving on. Today, what we want to have is, we want to calculate the 4D normal vectors beforehand, and then in the render code, interpolate those and somehow project them into 3D space where they make sense. Is what I'm saying. I made it to normal mapping on my own, but couldn't get SSAO to work. So in my comments, I'm completely stopping the development. Oh, it's fine. I'm talking. It's more discussion than development because the concepts are very complicated and abstract, and myself have not discovered everything. So I'm very keen on discussing shit instead of me just writing over here. Yeah, SSAO. What is? I'm not familiar with all the screen space ambient occlusion. Oh yeah, in real time. Yeah, well, see, those are things I should be familiar with because at the end of the day, I'm writing a 4D engine, but that needs a 3D engine in order to display anything. So I'm gonna have to get to those. So yeah, screen space ambient occlusion, that's a post-process technique, I believe, based on like edge detection and all that funny shit. I've done edge detection before in my computer engineering class, but yeah, it's very new, and I'm gonna have to read back on it. We are nowhere near implementing any of this though, so if you want to get a move on, if you want to get up on that, you're gonna have to do that on your own because I'm not gonna attend that anytime soon. First we do the abstracts thing, and then we do the image processing, one thing at a time. So yeah, what I want is improve my geometry 4D class over here by writing a function that is called compute normals, and basically just does exactly that. Okay, cell4, my cell4 class, I'm gonna store a normal vector in it. Yeah, there it is. I'm okay with abstract things. I'm okay too, in fact. Welcome. So yeah, vector 4, I used a flag that I called directional only. And this is used in matrix multiplication. Basically what this means is we ignore the translation part of the matrix. Because if you look at matrix 5, well, exactly like in 3D with matrix 4, matrix 5 in 4D is affine transformations. And we want to ignore translation, for example, with rotation vectors, of course. Rotation vector, normal vector, I mean, is directional only in the way that we should not translate the normal vector because it doesn't make sense. It's supposed to stay at the origin. It's a direction, as the name implies. and this translates to apply to vec4 over here. Well, apply to vec4, please. Okay, here you see t is the implicit fifth coordinate. If v is directional only, it's going to be 0, in which case we basically ignore the translation factor. And if it's 1, then if it is not directional only, then we just act as a normal vector. And just like in homogeneous coordinates, because that's what it is, it's for the homogeneous coordinates basically. And in that case, we just put a 1, and then at the end scale with it like that. 10 dot scale by 1 over t, of course. So yeah, we are gonna compute all of the good normal vectors, good old normal vectors. We are gonna do that using the very handy cross product 4D function that I already worked out. It's very ugly, as you can see. It's a bunch of stupid math, and basically the way that works is I'm gonna call on my good old friend MS Paint over here. Let's go, my dude, that paint bro. Bam, there. The way that works is wait, 1 over t could give you a division by 0. Could it? No. Let's see. Oh, I closed it. My bad. Temp dot scale by 1 over t. Well, it could, in fact, if v is directional only. Yeah, it could very well be a division by 0. Why does it not? Well, this it's been a long time since I wrote this. It's been like 4 months or something. I believe it's supposed to work every time. Can t ever be non-zero? Ever be 0? I mean, I believe it can, because this is the bottom row. Like this 20, 21, 22, 23, 24 is the bottom row of the 5 times 5 matrix, and is most of the time 0 indeed. Temp dot scale by 1 over t. Well, in fact, what I'm going to do is, if t is different than 0, I'm not sure why this hasn't broken yet. Oh shit, sorry. Yeah, paint. Get out of here. Alright, so yeah, sorry about that. As I said, t over here, right here, is this 20, 21, 22, 23, 24, which is the bottom row of the 5 times 5 matrix, and most of the time it stays 0 indeed. So because of that, I just added this guard, but I'm not sure why it hasn't broken yet. I guess it just, well, I'll take it. Yeah, I guess I was never using this with directional only vectors, because normal vectors I have never computed yet. I know it works because I've done the math on paper, but apart from that, I've never used it. So yeah, if t is different from 0, scale. All right, sounds right. Let's go back to this. Yeah, cross product 4D. So you can see in the cross product 4D there are a couple normal quote unquote cross product, which are the cross product 3D, between a little bit of coordinate swizzling over here. The point of it is that you can define how the fix doesn't have certain side effects. Well, we're gonna find out. The point of it is that you can define an n-dimensional cross product using the n-1 dimensional one. So go back to paint, Oink. And in fact, well, no paint, in fact. Sorry about that. Here, you can define the n-dimensional cross product between n-1 vectors. This is simply done in 3D, for example. 3D gives 2 vectors cross product. Easy enough. And the cross product, the theory behind it basically is that this thing over here gives the normal vector to the n-1 dimensional space, hyperplane, given by n-1 linearly, linearly independent vectors. This is what this is. A cross product is exactly that. So in case you are not familiar with any of this vocabulary, a normal vector is a vector that is perpendicular to a normal vector to a thing is the one vector that is perpendicular to every vector in that thing. So for example, if I pull out good old MS Paint for real this time, then we can see that we can say line plus here, right? That this plane, this plane here, it has a normal vector in 3D space. We just imagine that this is a 3D space, right? And because we are human, we can do that. So this plane has normal vector this thing. This is its normal vector. Because if we take any vector in the plane, such as this one, such as this one, or this one, or this one, you can see that the normal vector is actually perpendicular to all of those. So that's what it is by a sense. It becomes very much weirder in additional dimensions because in 3D you can go both ways. You can say that the orthogonal to this vector is the plane, or you can say that the orthogonal to the plane is this vector. It works both ways. And the way this works with the cross product is that you can, if you give n-1, you are in dimension n, right? It's an n-dimensional space. If you give n-1 linearly independent vectors, basically what that means is that you cannot make a vector out of adding the others. So yeah, basically, if you are familiar with it, it means that this is a n-1 basis for an n-1 dimensional hyperplane. And the cross product between n-1 such vectors is the one normal vector to the n-1 dimensional hyperplane that you just created. In essence, in 3D, it's exactly what I told you. Basically, like if I have, for example, this vector, like this one. Mouse, please. Okay. This one and then this one. Both vectors are part of the plane, and you can see that they are linearly independent because you cannot make one by multiplication of the other because it's only two vectors, right? So this one is not this one scaled, basically. It's an actually different vector. So both are not linearly independent. And if you do the cross product, then of course you get this vector over here, which is orthogonal to both, right? This is the definition. And in fact, this works because two linearly independent vectors uniquely identify a hyperplane, which is in 3D which we just call a plane. And the orthogonal to that is a single vector, and there we have it. And in 4D, however, it's a little bit more difficult because we can't see it, of course. So the way that would be is that, in fact, it's exactly the same, but it looks different because we can't comprehend it, but it's exactly the same. The way that will work is, aesthetics, very important. The way that will work is, I don't have 2 but 3 vectors. Take x, y, z, basically. And this uniquely identifies a space, a 3D space that we live in. And the 4-dimensional cross product will take all those 3 vectors and perform the operation, and it would give some strange vector. It would give us some strange vector that would look something like this, I suppose. I can only guess. And this strange vector is in fact perpendicular to all 3 of those. And it's the normal vector to our 3D space. And it only makes sense in 4D space. So I can only draw it like this because it's a 2D plane. And even so, it's very wrong because us humans cannot comprehend what 4D looks like again. So we can't properly imagine 4 vectors that are all orthogonal to each other, right? So, well, luckily we don't have to because we're going to just implement it and see how it looks. So what I'm doing here is I'm using this function cross product 4D. If you want to try and work out this formula, you will have to take into account the fact that to use the property, right? Oops. That the cross product between n-1 vectors is the only vector W, so that the mixed product between all of those is equivalent to the determinant of the matrix of the basis. You can look that up in the in the definition, in the Wikipedia page of cross product. If you did not understand a single word of what I said, that is fine. You do not need to. It's not relevant to our applications. So worry not. Worry not. And for implementation reasons, my cross product is going to be directional only because I'm only going to use it for that, of course. But it's not technically true, I guess. Okay. All right. So using this, we're gonna see in geometry 4D and do our compute normals. So we're gonna loop over the cells over here for in cells, and we're gonna just compute that shit. It's gonna be it's static, right? Yeah. All right. So vector 3 dot cross product. Well, first of all, c dot normal. Is that how I called it? Yes. C dot normal equals vector 3 dot cross product 4D of, okay, vertices is gonna use the vertices of the geometry, of course. Vertices c dot a. Stop, fucking, come on, computer. All right, vertices c dot b. Vertices. Wait, it's a cross product between 3 things, right? Yeah, I'm stupid. It's not at all gonna be that. We are doing a cross product between edges. Dot subtract vertices c dot a. That's better. And it's going to be, yeah, cross product between 3 edges, in fact, is what we want. So a to b, a to c, a to d, because it's a tetrahedron, so it has 4 edges. We just select 3 at random. Well, it has 4 sides, but it has more edges than that. But we just select 3 at random. A to B, A to C, A to D. That sounds about right. And then, why not normalize that? Hey, how about? How about we just... did I call that subtract, in fact? Is that what I called it? Sub. Okay, sub is the reentrant one. Okay, so I'm gonna use sub. I had the stupid idea of using different names than the Lime API, which I'm using under the hood, because I don't like the Lime API, the names that the Lime API has chosen. Fight me. Okay, so vector cross product 3D takes 3 vectors, 1 edge, 2 edges, 3 edges. Stop moving shit. Okay, and normalize the product, the results, because of course, normalize with length 1. Yeah, it returns. Okay, it's reentrant. So okay, yeah. And just like that, we are finished. Wow. Autocomplete would have saved you from searching that method. Yeah, it would, but I'm ready to go through the trouble of finding that in my files, because like I think I have it set on like shit like that, you know. I don't know if you see it in OBS. I'm gonna check real quick. I don't know if you see it in OBS, but if I do like cells, okay, you don't see it. You don't see it, but over here, right where my mouse is, there is a little window of suggestions, and it has the bad habit of getting all up in my biz when I'm writing something that is not in the list. So I find it kind of annoying in that sense. But yeah, I'm ready to go through the trouble of having to search my files. That's fine. I'm not in any kind of hurry. Did I delete something? No. Okay. I was worried. Alright, so we have our normal vectors. However, what we need to do is remember that when we are... I'm in a hurry all the time, yeah. Most people are. I believe that you should chill the fuck out, because if you're in a hurry, you're gonna do things wrong. And if you are calm and collected, then you will get the good ideas all the time. The correct ideas at first try is what I mean. Okay, so I have computed my normal vectors. Then we have to remember during the rendering, right, that we need to actually rotate the normal vector as well. Okay, so how to achieve if you have a boss in your back wanting results? Yeah, but you must not mistake being in a hurry for being fast, because if you are fast, then it's fine. But if you are in a hurry, you are bound to rush things and do things wrong and like forget edge cases and shit like that. So you can be fast, but you have to draw the line between being fast and rushing shit. Okay, so yeah. Okay, so here is our one big problem. We have 4D normal vectors, which I did not calculate anywhere, but I'm going to do it now. From 3D in the box class. Okay, box class. Geometry dot compute normals, just like that. Oh yeah, by the way, in case you didn't realize, the cross product operation in 4D is very, very expensive. You have to do 4 cross products and 4 dot products between all different vectors that are basically extracting components from a 4D vector, and that's like very expensive. So we only want to do it once basically, and then we rotate the results around instead. I forget edge cases if I have to search for method names by short time memory. Yeah, well, I don't have that problem, so that's also part of why I don't use auto-completion. That's why I don't miss it as much, I guess. Okay, so we have our normals. What do we do with them? Well, here is the fancy matrix can do that. Yeah, well, any matrix will do. Like our 5x5 matrix that we compute over here, exactly what we want. There's another problem though. Once we have rotated the normal vectors correctly, the problem is that what do we do with them? Because right here we intersect tetrahedra, and then we only compute normal vectors afterwards, like on the triangles. But what if I have interpolated the normal vectors, right? What if I have that? What if I want to keep that? Like in the same way that on the 3D sphere you want to have like, okay, paint, I require D once more. Okay, so let's say that you have a sphere, a black sphere in fact. Boink. This is a sphere in 3D. It has a shine. Bam. And of course you want your normal vectors to look good, so you have like it's in fact triangles, right? It's all facetized. But we don't need that. We want to interpret normals so that it all looks good. So you have normals like that, kind of like that in a way, like that over here. All right, something like that. But then that's fine because you only have to do like one normal vector per vertex, and then OpenGL will interpolate bilinearly your normal vector over all the sphere, and then your shaders will be able to use them. But what if we have 4D shit? Because in that case, OpenGL does not do any interpolation because it's not being fed the actual 4D geometry. We intersect it first, and then only then we use it for we recalculate the 3D normal, because it's a per triangle thing and not a per tetrahedron thing anymore. So I'm thinking, this is open, right? I did not implement this. I thought about this a little bit, but then I thought I'd keep it for the stream because it's an interesting question to ask. What do we need to do? Okay, where did you come from? So what we need to do is, I'm guessing, right? It's a thought. We have, well, yeah, I'm thinking that I did something wrong here, because in the geometry we compute normals on a per cell basis instead of per vector. So that's fine, we can do that. Something else we can do is directly give an array of vectors, of normals, I mean, and 3D, which is going to be optional. And 3D is going to be an array of vector 3, which are going to be normal vectors. And blah, blah, I'm thinking. I was heavily influenced by the 3.js hierarchy when I wrote this, by the way. So, if anybody's familiar with that, does 3.js have does 3.js keep an array of normals at the geometry level instead of the face level? Is what I'm wondering. Because if we want to do per vertex normal, then we don't currently use 3.js for my job. Well, there you go. Can you tell me that when you load an object, a wavefront object or anything, usually normal vectors are defined per vertex instead of per face, right? So I'm wondering how does 3.js use that? I don't remember. I've used the first demo uses 3.js, but I forgot how it works. It's been a while. Geometry. Hello, geometry. Please. Where art thou? I need you. Core. Geometry. There. Okay. Map normals, no. Blah blah blah. Morph normals, no. Morph normals have similar structure as morph targets. No, that's not what I want. Okay, I don't think 3.js holds normals on the geometry level. I would have to look at it in my code. There is a way to easily make a model from vertices and faces, and then 3.js converts it into a buffer from .js. Yeah, that's not what I mean. What I mean is, does 3.js keep an array? Where does 3.js keep normal vectors? Is what I'm asking. Because if I remember correctly, it has a face3 class, and that face3 class has a normal vector. Yeah, vector showing the direction of the face3 is calculated automatically. This is the normalized cross product of two edges of the triangle. Okay, so that is exactly what I'm doing. Oh yeah, and then no, yes, well, oh yeah, and then it has vertex normals property. Like array of 3 vertex normals. There, that's what I meant. Okay, so it's all at the face level. Okay. Been a few months since I did that part, but short anyway. No worries. Okay, so we are gonna use the same approach, and instead of doing that, so we have a normal of the face, but then we also have a vertex normal. Okay. This is gonna be for interpolation purposes. For example, if I want to have a 4D sphere, then I'm gonna approximate the normal vector field by basically interpolating normal vector values at the vertices. So normal A, I guess. You just copy paste that shit, like it's hot. Bam, normal A. Set normal A. Yeah, normal A, boink, and then normal B, C, D. It can be null, in fact. It can be null because in case we don't want to give it like any vertex to interpolate, I mean, then it doesn't matter. A, B, C, D. Yeah, forgot one. Oops. Yeah, in case we don't want to actually give the engine any vectors to extrapolate, like for example in my cube demo, there is no need to interpolate normal vectors, so we just don't use them. That is very much fine. A, B, C, D. Yeah. Okay, so indeed the normal is it's still a normal vector to the face, to the 3 face, which is called a cell, as the name implies. And a cell is a tetrahedron, so this is the normal to the tetrahedron, but then we can store per vertex normals. Per vertex normals for interpolation purposes. Just like that. Normal A, B, C, D. Because I have, again, A, B, C, D here, like all matter of being consistent. And I don't want to use, I don't want to allocate an array just for that. Oops. Well, I mean, we could, but then I can't use direction only. Okay, it doesn't matter. So yeah, c dot normal is that. Okay, so if we give a 3D array of things, then in that case, what I do is, okay, for every face, yeah, what I do is, I want to push normal vectors of everything based on how they were extruded. So I'm gonna build, ooh, that's shitty. And okay, I'm gonna build an N4D array, which is gonna be a new array of vector 4. It's gonna hold all the 4D normal vectors, and we're gonna push things into it. It's gonna have 1 per vertices. Okay, so yeah, if we have if n3d is not null, basically. If n3d is not null, n4d dot push new vector 4, which is basically going to be, okay, we need to iterate over this. Wink. Okay, so v3 index var v3 is v3d of v3 index. Alright, the variable names are kind of shitty, I realize now, but we'll be fine. Don't you worry. Okay, n4 is gonna be, no, n3 in fact, is gonna be n3d of v3i index. Okay, so this is gonna be a vector 3, I mean, vector 3, there. And with, okay, so here's the thing. How do we know how do we extrapolate the 4D normal out of the 3D normal? So in order to answer the question, let's look at Paint. Yo, ain't that a thing? Okay, so let's go back 1 dimension down, and let's say we have this cube, the square, I mean, good old rectangle. Okay, as to not put unnecessary constraints on my drawing. Okay, rectangle, bam, rectangle. So we want to extrude it, have it in 3D. So what we do is simply copy it and join the, oops, copy it, paste it, join the edges, bam, easy like that. That's kind of embarrassing. Okay, over here, no. Damn it, Paint, you do one thing, like, can you do it correctly, please? Okay. Yeah, just like that, and join the edges. Bam. Ugly, but doesn't matter. Okay, we have our 3D box. Okay, then we have to consider the 2D normal vectors. The 2D normal vectors, they look like that. I'm gonna draw in red the original box, the OG, like that, and then we are going to consider we're going to consider the 2D normal vectors. So they look a little bit like that. This is one. Again, in a 2-dimensional object, again, is best described by its boundary. And the boundary of a 2-dimensional object is 1-dimensional. So this is why we have a closed curve over here, which is a rectangle, again, a non-filled rectangle. So all our normal vectors are this. But then can we extrapolate those to know the 3D normal vectors? Well, you see that we have extruded edges, like the red. We have extruded them along the Z direction, kind of like that. Wink. In that direction. So as such, the normal vectors, they stay orthogonal to that direction, to the direction of extrusion. So as such, the new normal vectors will be basically, if I draw like in red, the new vectors, nx, ny, and z, are going to be, in green this time, nx, ny, 0. Why? Because they are orthogonal to the direction of extrusion. The direction of extrusion is the z-axis, basically. So, because they are orthogonal to the z-axis, they should have a 0 z coordinate. But apart from that, they are identical. So that's why we keep the same green x and y coordinate. But we add an extra 0 because it needs to be orthogonal to the direction of extrusion. But then we have a couple more. We have faces that weren't faces before. Case in point, those ones. This here, this face, was not a face before, because in 2D, quote-unquote faces were actually edges. But now we are in 3D, so this becomes a face. And this is a major flaw in my code right now, because I'm not taking care of this properly. The good way to do this would be to take this 2D surface, you do a 2D Delaunay triangulation to give something like that. And then this is a face. This becomes a 2D thing. And then we can have normal vectors. And then those normal vectors are along the direction of extrusion. So I'm going to give them blue vectors, blue normal vectors in that direction, just like that. Wink. And again, same thing the other way over here, like going outwards, right? And those are gonna be like directed by the direction of extrusion. So as such, nx, ny, and z is actually 0, 0, and plus minus 1, depending on which one we consider. So here we have successfully extruded and interpolated all of our normal vectors. But then you ask, oh wait, but what about, that's face vectors. That's not vertex vectors. The face normal vectors instead of per vertex normal vectors. And well, I haven't exactly found a way to make that consistent, in fact, because what if, right? What if I have a brown vector? And what if it's supposed to go a little bit like that? Like in 2D, right? In 2D, it's supposed to go like that. Okay. And there's no definite behavior to be had, I mean, because how do I know if I want to make a sphere or a box, right? Well, how do I know if I want to interpolate the normal vectors to make that look like a sphere or a box? And it's not consistent. So in fact, we are only going to extrapolate the 4D vectors, or what we can do is assume that we always want to extrude in a cubic fashion, and as such we just extrapolate exactly like that. Use this one, basically using the fact that every normal vector stays orthogonal to the direction of extrusion. This is, I think, the most logical way to do that. If anybody has any counter arguments and wants to try and think of a better way, then by all means tell me so, because that's the point of it all, as you will have noticed. So yeah, another way I've been thinking of doing that is basically have a kind of I'm trying to think of a word here. Kind of bend the vectors outward from the center here, the center of the shape of the 3D shape. Bend them kind of outwards in that direction, like that, poink poink, in order to have a kind of quote unquote go away from the center feel, and that would give normals pointing away from the center. But again, I don't know how. There's no way of knowing if the programmer wants that or not, except by being told so, which I don't think is really user-friendly by any means. So yeah, instead what I want to have, what I think I want to have is basically take a 2D object, make it into a box. If it's a circle, it's gonna make a prism and now not a sphere. And if you want like more specific 4D objects, you're gonna have to tessellate them yourself. And I think it's a fair trade because there's only so much you can automate, right? So yeah, I'm probably gonna do that. I'm gonna do that right now, in fact. Gonna do that right now. So N3D is gonna be a per face and not per vertex. Oh well, no, it's gonna be per vertex. Okay, per vertex is what it's gonna be. And as such, we want to fill normal A, B, C, and D of the cells. So what we do is per vertex, yeah. So N3 is the current normal vector, and again, what I said is we apply the rule that we had in our Paint program here. Paint, I said, okay, which is this one. Keep all the same coordinates that you already had and add a 0 to the mix, because normal vector is orthogonal to the direction of extrusion. So let's do just that. N3.x, N3.y, N3.z, 0. Put z, 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 I don't know. Ooh, okay. I've been told that it was like alternatively what z or z. Which one is it? Which one should I use? I don't even know. I demand answers from all of you English speakers out here. Is it Z or Z? I keep using one then the other, but I've been told to use one and then I've been told to use the other, so I can't really know. Alright, so this is our 4D vectors. And 4D.push new vector 3 is 0, blah blah blah. Okay. And yeah, and because we are extruding both vectors at both ends, both vertices at both ends of the extrusion will have the same normal vector. So we just take that, copy it. Boink. Yeah, and also exactly the same thing except with the minus. Well, without the minus, I mean. Boink. Like that. Okay. Okay. Alright, so we have our normal vectors, and then we have to push them. We have to push them to those. It's gonna be long and boring, and because of that, I'm gonna write a little helper function, bro. Private, well, function push, well, set normals. I'm gonna take a cell. What else? What do I want to do? I want to set normal A, B, C, D to a couple of indices. So as such, I'm gonna take A. Well, NA is int, and B is int, and C is int, and then D is int. There. Oops. Is that the best way of doing that? I don't know. Well, I kind of wanna have an array of normals. I'm gonna diverge from 3.3gs and actually not have that because I think it's redundant, and we are gonna loop to the faces anyway and the vertices, so we might as well just have an array of normals over here. Vertex normals is gonna be an array of vector 4, vector 4 equals new array. Poink. Vertex normals. Okay, so then we don't need that because it's right over there in here. Yeah, replace basically N4D with vertex normals. What was that? Phone, hello? Yeah. Okay. Poink. Vertex, shit. Okay, try again. Without the fucking up. Vertex. Poink. Vertex normals. There you go. Alright. So we have our arrays of 4D normals that we extrapolated from n3D, from the 3D normals we gave it. So I kinda wanna try that and build a sphere. I'm gonna build a 3D sphere, and we're gonna see how that goes. We're gonna use this from 3D. We're gonna build a 4D prism, which is a sphere-based prism, basically. Like, you knew the regular prism, not prism, cylinder. Sorry, the 4D cylinder, which is a sphere-based cylinder, and in 3D you knew the cylinder, which is a circle-based cylinder. And in 4D, we're going to do the sphere extrusion to give a sphere-based cylinder. It's going to be weird. Oh, it's going to be weird. Okay. Yeah, because the cylinder, the 3D cylinder, depending on how you look at it, you can either see a circle or a rectangle, depending on the angle. And then in 4D, you can see either a box or a cube. Well, depends. A box or a sphere. It's going to be great. It's going to be great. We're going to see a sphere move and morph into a box if we get that done. Okay, vertex normals is that. That's also one good way of seeing if interpolating vertices work. Because a sphere is very good candidate for having a per vertex normals instead of per face. So yeah, we're going to see how that goes. We're going to see how that goes. Yes, that's English. Hello. Vertex normals, I guess we don't need to do that at all. However, we can still compute normals to do, like, for whatever purpose if we need them. I don't know. I don't know at all. Okay, set normals is not needed then in the end. Alright, so we worked out our interpolation rule, and that's good and all. Did I not make a mistake? I don't think. Okay, vertex normals that push blah 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 blah. Alright. Okay, so we're gonna generate geometry. We're gonna do a 4D sphere class, which is very much gonna be the box, in fact, most of it. How do we call that? Cylinder 4D? Spherinder. There you go. A spherinder. It's a spherinder. It's real. Spherinder hype. Right, spherinder is gonna be exactly that. Okay, x, y, z, z, w. Width, height, depth, depth is not going to be that anymore. There's going to be only depth and radius. Radius. Wink. Color, why not? Geometry, of course. Cube faces. Okay, here comes the stupid part. I'm going to generate those on the fly, as well as the vertices. Faces, array of int, yeah, they are, in fact. Okay, I'm gonna generate those on the fly. Because no array. I'm gonna have a static like init function. Or I could just abuse the good old hacks accessors. Default, no, get is get and set is default. Or never, in fact. Okay, and then, okay, so that's one way that hack's pretty cool. You can have custom accessors like that, and then you write the function, static private function, get faces. It returns an array of int, of course. Okay, so if faces, okay, it's an actual variable, of course, so we just add metadata. That's just to say that, to hack that it is actually a face, a variable, I mean. If faces equals null, then just feed it with the corresponding data. So we're gonna take care of that later. Create the sphere faces. Yeah, it's gonna be triangle faces. Okay, so this is a little bit boring. I'm gonna do a bunch of 2D math to generate a sphere mesh. So in the meantime, sorry. You can just ask any questions that you have in mind, if you so desire. This is the time to go cray-cray. Feel very much free to ask anything you want. Default and set error. No, not default. Get static. Well, static private function get vertices. Same deal. It's gonna be an array of vector 3. Same deal over here. Okay. Create the sphere vertices. Oula, hey. Create, I say, the sphere vertices. Wink. The sphere faces? No, spheres faces. Right. So I'm not gonna do it in any interesting way, really. Oh shit. I'm not gonna do that in any particularly optimized way because I want. In particular, I'm gonna replicate like how many times? How many times? That's how many times. Static private var samples. Well, static inline static private var samples equals how many vertices should our thing have? 20? 32? 32 by 32 sounds about right. Okay, so yeah, that's gonna be exactly as much for j. Well, okay, so we're gonna do that on spherical coordinates, and as such, it's usually phi and theta. Theta is verticals, phi is horizontal. So theta step in 0 to step samples, and then for phi step in 0 samples plus 1, I believe. Yeah, plus 1 for texturing. Okay, so var. Okay, first of all, theta goes from pi over 2 to minus pi over 2, if I'm not mistaken. Yeah, it's on the y-axis. So yeah, from pi over 2 to minus pi over 2. Or we're just gonna do it the other way around, maybe. Mat.pi over 2 minus theta step over samples. Oops. Times 2. Times math.pi over 2. In fact, hey, no, not dot pi. Okay. Does it have to reach? Yes. Okay, so plus 1, in fact. Okay, so this is just creating a sphere mesh. Because I'm too. Well, I could download it from somewhere, but I would have to write a loader, and I can't be arsed. So we're just gonna generate it. It's okay. So theta goes from pi over 2 to minus pi over 2 in steps of, well, 1 over that, and phi is going to be from 0 to 2 pi, phi step over samples times math.pi times 2, and that's going to be the vertices. Yeah. If vertices equals null, then we generate them. All right. Vertices, oops, equals new array. Hex is gonna infer the type, and then we push those things. Okay. So var v equals new vertex 3. Vertex vector 3. Okay, what's it gonna be? Radius is 1, obviously. Radius is 1. Yeah, radius is gonna be 1. Yeah. Vector 3. X. Okay, spherical coordinates. Let's go. X is gonna be sine of theta, if that's correct. Because when theta is, well, no, it's going to be sine theta cosine phi. Yeah, I'm just going to look it up. I'm going to be the smart ass over here. Spherical coordinates. Oops. Let's go, Wikipedia, do your worst. Okay, give me the thing. Okay, x is r, which is 1, sine theta cos phi. Okay, did I switch the usage of two things? I did not. Okay, so I just a moron. Sine theta? Oh no, I did it wrong. I did it correctly, I mean. Cool. So that's going to be x. R is always 1, again. When we are building a base mesh, it's always going to be centered and normalized because we apply the transformations in the shader using a model matrix, of course. So R is sine theta sine phi. And Z is math cos theta, of course. Just like that. Okay. So we have our thing, push, vertices dot push v. Oink. Okay, so that should create our mesh. Oops, sorry about that. So we could just check it out. We will, in fact. Faces equals new array, period. Okay, so we're gonna check that with like 4 samples. And we'll see how that goes. Okay, so gel buffer, gel program, gel position normal, all the same things. Solid vertex, blah 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 blah, solid fragment, blah blah blah. Okay, so it's not that anymore. R is gonna be oh yeah, x, y, z, w. I'm stupid. X, y, z, w, of course, but this is what goes. This is what stays in turn. Radius equals underscore radius without the parentheses. Okay. Duth equals duth, color, blah blah blah. Geometry dot from 3D vertices cube faces duth. And it's not that anymore. It's vertices faces duth and compute normals because why not? Programs is blah 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 blah, all the same thing. Okay, render is same thing, blah blah blah. Normals, push triangles, cut product, intersect them tetras. Okay, that's the same, it's all the same. I think the render function is actually reusable. We're gonna write an object class when we want to care about clean code. It's not for now, not for now. You say blah blah blah, offset is that, gel buffer, blah blah blah, okay. Okay, sounds good. Surrender. We're not going to display it anywhere, we're just going to create it to see if the things are correct. Okay, does the surrender use OpenGL in the new? Yes, okay, so we can just do that. Var s equals new surrender, centered on 0, 0, 0, 0. Radius of 1, in fact, a duth of 1 as well, and a color of red. Of blue, because our box is already red. And we're gonna trace s.geometry to be sure that not geometry, I mean well, first of all, we're gonna make that not private because then we can't access it. And we're gonna draw we're gonna display the vertices just to be sure that it's actually being correctly generated. Let's see. Oops, that's not what I wanted. Terminal I wanted. Okay. Oops. Let's see how that goes. So yeah, just regular spherical 3D mesh, 3D sphere mesh. In fact. Oh boy. Oops. No. This field cannot be initialized because it is not a real variable. I forgot and at isvar. This is what happens when you forget isvar. This is what happens. Also, those are public. Cannot access static field vertices from a class instance. Oh, yeah. I don't need to instantiate that at all. My bad. Surrender.vertices. There. Do that again. An access field or identifier faces for writing. Why not? Oh yeah, it's no, not never. That's one like very fade shade of hacks. A non-identifier width. Oh yeah, the okay, we don't need a render function. Get out of here. We don't need that at all. Oh, of course. Of course, of course. They're happy? Happy. Cool. Let's go. Alright. Okay, so we have a bunch of shiz. So let's see how that goes. 1, 0. So we're expected to have the top, right? The top one. 1, 0, and nothing. Okay, the x coordinate is first, which is weird. Then slightly like x equals 0, y equals 1. Okay, that's weird. S dot blah blah blah. Minus 1. Okay. Oh yeah, it's making a full turn. Okay, fair enough. All right. Okay, cylinder. Okay, fair enough, cylinder. And face is gonna be like for every vertex display a quad, basically. So yeah, oops, leave that. And for every vertex except the very last ones, yeah, okay. For j in 0 to vertices dot length. Make sure the vertices are built. Oh no, well, I'm stupid. Samples. I created that for a reason. 32. Why not? For j in 0 dot samples. Well, we could just display points, right? We'll try it out. We'll try out the sphere render. We're gonna have a render function, but it's not gonna do any of those things. Well, yeah, it is. Okay. We're gonna modify the render function so that it displays points. First of all, draw raise is gonna be points. Starting at 0 with temp.length. Yeah. Okay, so what do we do? So basically just exactly that. Without all the attributes, we don't care. We need that, not that, not that, not that, not that. And just a stupid JFrag color. It's gonna display it. Oops. Oh no. It's gonna display it in blue. As I said, we're gonna cheat because I can't be arsed to put extra uniforms just for that. Alright, so this is gonna be plain blue. We're gonna display dots basically, and we're gonna check that it actually does a sphere. Alright, a position, a normal, it's gonna be -1. Doesn't matter. UMAT doesn't matter also. UMAT does matter. My bad. No, it's PMAT in fact. UMAT is blah blah blah. That's fine. That's not fine. Radius, radius, radius. Okay, drop that. Doesn't matter. There. Have a couple rotations if you want. Translate X, Y, Z, W. That's actually good. Don't rotate. Just translate. Hey, it rhymes. Vertices 3D push triangle is the same thing. Well, yeah, we don't have a 4D object, so discard all that I just said. Wink. Intersect nothing. In fact, here, bang, 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 bang. Alright, don't intersect shit. Offset equals vertices 3D dot length. We're just gonna push like the actual vertices array and just draw points, and we see if it's correct. GL buffer, we're gonna do vertices. Oops. Vertices dot length times 4 because it's a float 32 array. Vertices, dynamic draw, it's going to be static. Well, it doesn't matter, but yeah. Do things a little bit good. If gel position thing is a 3, yeah, there's no normal, that's gonna not work. PMAT, yeah, gel UMAT 1 false PMAT, that's correct. And draw points, okay, this should be good. If and only if we add a sphere in there. Rixvar sphere in there, which is actually a sphere at the moment, but that's fine. You know, new sphere in there. X, Y, Z, W. What else? X, Y, Z, W. Oops. New, please. Okay. X, Y, Z, W. Radius, dooth, C. Radius is 1, of course. Dooth is 1. C is blue. So we don't have to change it later. Then surrender.render. Okay, let's see what kind of delicious errors we get. I did not think this through when an identifier offset. Do I need that? Is that a thing I need? Where? Oh yeah, here. Well, we don't. It's a joke. We don't need it at all. And count. Oh boy. Oh, temp. Yeah. Vertices, okay. Is what you meant. This should be good. God damn it. God damn it. Vertices equals all of that. Okay. Where could that not work? Oops. Stop. Trace. Surrender.vertices. Couple of crashes, of course. So is programming. You cannot access static field vertices from a class instance. Yes, I've done this error already. There, big S. How does that make you feel? Okay, it crashes instantly. I'm not okay with how that is crashing instantly. Okay, let's go and see how Assman doing. No, let's see how the OpenGL thing is used. Draw arrays. Mode first count. Okay. Draw arrays is what I'm looking up. OpenGL for reference. Yeah, in case you don't know, crashes with error messages are the worst. Oh boy, tell me about it. I have learned to loathe lack of error messages, but we can rise above. We can will. I'm looking up draw arrays as we talk. Yeah. Haven't specified blah blah blah. GL line strip blah blah blah. No. GL points. Line strip, line loop, lines. Okay, points is what I want. I'm guessing I'm misusing some attribute vector or something. Vector A position is gonna be vertices. Yeah. Main is just gonna be that. UMAT times vec4 A position. The frag color is just a solid color, doesn't matter. Oops, sorry. Okay. XYZ blah 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 geometry dot form 3D compute normals program equals GLTs. Okay, it's not crashing in new, by the way, so that's stupid. GL use program. Did I create that program first? I did. Okay, solid vert solid frag is this one. Cool. A position, a normal. A normal is not used, and as such, it should return -1. So that's fine. Use program, identity, translate, bind buffer, vertices.length times 4, and new float 32. Oh, am I? Yeah, this is not a float. This is not a float at all. Times 4 times 3, and vertices.map. Yeah, I know what that is. That's stupid of me. Vertices is an array of vectors, and I should be giving it arrays of floats. And we are going to build that, in fact, just now. For v in vertices, temp.push v.x yz. There. And we give it temp.length and temp period in fact. Blah 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 temp.length. There. Ain't that better? It should. Hopefully. Okay, it doesn't draw anything, but at least it's not crashing anymore. Well, we have our $40, but that's all. Okay, do I need anything else to draw points? GL points. I'm gonna, if anybody knows, by the way, does OpenGL take anything particular to draw points? Oh no, wait, that's because it's centered. Yeah, it's centered on the camera, so I can't see it. So instead, I'm gonna subtract. I mean, like 3, and slightly to the left. Should be better. Yeah, I'm wondering if OpenGL needs like any hint as to how to draw points. Like if okay, there's a sphere. Oh, that's pretty good. You can see it like over here. I actually want to like OpenGL dot width. A GL point size. Okay. Specify the diameter of rasterized points in pixels. I assume. The initial value is 1. Okay. Okay. Alright. So it's just GL point size. I'm gonna put that in main real quick. GL dot point size 3. Why not? Oops. Okay. Yeah, I'm not sure you could see it. Has no field point size. What is this now? Point size? There's no field point size. How is that? How is that a thing? Which OpenGL is it? GL 2.1. Oh, that's kind of old. OpenGL 4 point size. GL point size. OpenGL 4 reference pages. Contains size of rasterized points in the vertex, tessellation, evaluation, and geometry languages. A single global instance of the GL per vertex name block is available. Okay. Point size. Alright, in the vertex shader then. Let's do exactly that. GL point size equals 3. Is that okay? GL point size. We'll just find out, I guess. So it's not here. That was OpenGL 2, basically. Okay. It doesn't change anything. Cool. Exactly what I wanted. In the vertex blah 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 is an input that receives the intended size of the point to be rasterized in pixels. It may be written at any time during shader execution. If GL program point size is enabled. Okay. Alright, we have to enable that. Thanks for telling me documentation. Enable GL dot program point size. Okay. Finding out cool stuff about OpenGL in the process, and that good. Has no field program point size. Well, of course. Program point size? Line, please. Did you not specify program point? Vertex program point size. Okay, so it's different. Let's see. Yeah, because Lime is a framework. Ah, much better. Okay, we're gonna move this sphere along a little bit because it can't exactly be seen very much. So -1. Yeah, as I said, Lime is a framework for hacks that exposes various OS features. Ah, ain't that good? It's a sphere. It works. It's working pretty cool. But is it like? I feel like it's only a part of the sphere, isn't it? I'm going from like, yeah, maybe. Yeah, Lime is a framework. I'm getting there. Lime is a framework that exposes cool things to hacks, such as, for example, the OpenGL API, and we can use OpenGL in hacks thanks to Lime. That's pretty cool. And this is why this is the first reason why I chose to do that, because it's made easy by line. And basically the fact that you are doing hacks is transparent, and you can use the conjunction of hacks as like flexible data types as well as just regular good old OpenGL. Okay, so I think I'm not actually rasterizing enough points here. Either not rasterizing enough, or temp.length is the number of floats. Either not rasterizing enough or not generating them properly. Specifies the number of indices to be rendered. How many indices, you say? Temp.length is how many? Okay, well, sounds about right. Okay, so I'm assuming that I'm not generating them correctly then. Or maybe I should just rotate pmat. That's fine also. Yeah, let's have pmat rotate a bit depending on the time, and we can see where we are failing, is what I'm saying. Okay, so again, another Lime thing. Lime has its own math classes, including matrix 4, so we're going to just do that. Append rotation is what it's called, or prepend rotation, in fact. Yeah, that's going to be much better. pmat.prepend rotation. Oh no, because it has to be a model view. Annoying. Okay, I'm gonna rotate it here. No, never mind. Okay, I'm just gonna check the code and believe that I'm right. It's gonna be enough. Vertices. Theta goes from, yeah, plus p/2 to p/2. Pi/2, I mean. Trace theta, track, trace. Trace theta, trace phi. And that should be enough. Sorry, I'm taking a while over like not so interesting things, but then again, well, it's natural. It's a natural progression on my end. I did not plan everything through. Okay, phi is indeed reaching pi times 2, and going from 0 to pi times 2. Okay, and theta is indeed going from is indeed going from pi/2 to minus pi/2, I believe. Yeah, that's pi/2 roughly. And that at the bottom was in fact over here minus pi/2. Okay, so I'm not brain dead, at least. That's good to know. And this, okay, I'm assuming then that the sphere is being clipped in some way. Not sure how or why, but yeah, we're gonna have to do. Or we are not just not drawing enough points. That's possible. I'm not too sure on how that works to begin with. I'm always very confused by OpenGL's ability to just be weird. Like GL points, how many indices? What are indices? Like if I do that times 3, am I boned? I don't know. Let's try it out. Let's see, we just find out. No, it doesn't actually change anything. What ends that thing? Well, because yeah, I'm wondering if I have, in fact, only drawn a half sphere. It doesn't matter. And then we're gonna move on to faces. Faces. Okay, so it's basically the same loop. Boink. Yo, stop. Okay. Instead of theta and extra, it's gonna be J and I, sorry. And we're gonna go all the way up to, but not including, J is gonna be from top to bottom, and I is gonna be not from top to bottom, in fact. Just rotate the sphere as you do with the cube, that way you see if things are missing. Yeah, well, here's the thing. I'm not applying a matrix in the object space. I'm just pushing it. Oh, well, I could. Yeah, no, I'm just stupid. Yeah, of course. Of course I should do that. I know, because I'm translating it. I am translating it like in ugly fashion right here. Okay, scratch that. Put that on hold for a while. Wink, wink. And instead, use the good old over here. There. UMAT equals new matrix 4. Yeah, I'm stupid. Sorry, my brain, I just like brain fart. It happens. And a position X, Y, Z. Yeah. And we're gonna have like -3, -1. Like we had. Okay. Rotate like that. Upon rotation, blah blah, normalize. Yes. And then PMAT. It's gonna be like UMAT times PMAT. There we go. UMAT times PMAT. Do I have my own matrix 4? No. Okay, fair enough. Or it's actually PMAT times UMAT. Now that you realize. Okay, this should be good. It should be golden. And then the theta step. Yeah, never mind the faces. Never mind the faces for now. We don't need those yet. But if OpenGL vector 4 should be lime dot heck. Rad vector. Yeah. Lime dot blah 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 blah. Yeah. I'm using concurrent definitions of the same types. It's a bad habit. Sorry. What? Cylinder.hx235. PMAT times UMAT. What? PMAT is a matrix 4. And UMAT is also a matrix 4. What? How does this give? And I don't understand. Okay, wait. Lime, please. Append is what we want. It gives a void. Shit. Append scale, append blah blah blah. Multiply is what I want. Can I not multiply? Oh no. I can't multiply in a reentrant fashion. That's shitty. Doesn't matter. UMAT dot append PMAT, and then just use UMAT. There you go. Yeah. Is this okay? Okay. Okay. So I am missing what? So I am missing half of the sphere. How is that? Juste. Merci. Non, non, pas sur les dents. Sur. Ouais. Alright, so I am indeed missing half of the sphere. How did that happen? Where did it go? That's weird. In case you didn't understand from what I've said. Okay, wait. Theta step. I mean, what? Sine of theta times cosine of phi, sine of theta times sine of phi, and math dot cosine of theta. Is it theta? Spherical coordinates? Yeah. What? How is this? Yeah, okay. So theta goes from, I'm guessing, not what I was thinking, from 0 to pi, of course. Of course, of course, of course. 0 to pi. Exactly that, okay. Maybe. Yeah, okay, there we go. Okay, I know I'm good. I know my math. Sure. Right? Don't I? Okay, sphere. There you go. Much better. Okay, I think I left the ×3. Yeah, that's not needed at all. That's a mistake on my end. That's why there was a single pixel in the middle. Yeah, there is a dot at the sphere center. That's because I left the ×3. And it was not the rest of it. I removed it. Let's see if it's fixed. It should. No, it's still here. Okay, I'm not 100% sure on what that is. Alright, don't know, don't care. It doesn't have to. Dot center is still here. It is, in fact, still here. Okay, we should have like 33 squared samples. I'm not sure why there would be a 0, 0, 0 vector in there. No idea. It doesn't. Yeah, we'll just move on. Alright, as for the faces, well, the faces are easy. We just go, like, there is basically one square per vertex excluding the last row. Samples not +1. And then just push triangles. New array of int, yeah. Push triangles 2 by 2, basically. We're gonna have to do some shitty math using modulus and shit like that. Okay, faces dot push. First of all, I and j. So wait, let's see how we pushed it. How we push the things. Alright, so it's according to z. Oh, that's gonna be confusing. Okay, I want it to be same y. Let's see how that goes first. Yeah, because I want my my 3D axis system to be computer graphics axis system and not mathematics axis system, because in mathematics z is pointing upwards and I don't want that. Okay, so now it's fine. So y is constant over phi, so that's what we want. Okay, so j has the role that theta has, so j is going from top to bottom, and I is going from left to right. So we want to push our triangles. The sides don't matter because the orientation doesn't matter because I'm doing double-sided triangles. So what you do is push I times samples +1. No, j times samples +1 plus I. Yeah. What else? Next one is I +1 modulus samples +1. Next one is wait, no, that's not the next one actually. That's like j +1. Okay, that's the diagonal, and before that I want the j +1. Alright, that's better. That's the first triangle of the quad, and then second is basically the rest. Poink. Alright, so this is like top left, this is bottom left, this is bottom right, top left, bottom right, and then we want top left, so that's it, bottom right, and top right. It's I +1 modulus all of that, and j, period. Okay, so that should be it, if I'm not mistaken. So faces, okay, let's see. So we keep those, and then draw elements. Well, not points anymore. Triangles. 0. It's still gonna be blue. It doesn't matter. Not shaded also. Gel the triangles 0 and temp not length. Oh well, one trick we can do, in fact, is wait, solid vertex. We still need the position, right? Yeah, we don't need v position. We can have v normal. Basically, v normal is just minus a normal, minus normalize a position, because it's a sphere. So the normal is actually the position. Normal is minus position, or it's actually just plain position, not even minus. Then we can use the normal to do some lighting. How about that? Oops. If I'm not mistaken, again. V position. Oh yeah. Oh yeah, of course. V position equals a position. U mat times a position. Oh yeah, here's the shitty thing. Okay, no, it's not. It's more trouble than it's worth. Just forget the normals. Because I have to rotate the things and it's shitty and no. Forget that. Forget it. If we have a hole-less sphere, it's going to be good enough. Okay, draw elements. I don't remember the thing. Fuck, no. Okay, draw elements. Mode, count, type, offset. Okay, mode, triangles. Count, faces.length. Yeah. Type is gl.unsigned int. And offset. Hang on, what? Draw elements? Mode, count, type, offset. Hang on. I'm confused. Draw elements, I thought they void indices. Yeah. What? Draw elements. Yeah, GL draw elements. I'm having like different documentations. Okay, it doesn't matter. I'll take care of it. Mode, count, type. Okay, mode is triangles. Yeah. Count is faces.length. Type is unsigned int. And indices is new uint32 array of faces. That should do. Hopefully. There you go. Very good. And we can even see with the aliasing that it is indeed rotating. Alright. Pretty cool. And if we do like a stupidly low sample number, then we can have basically a cube. Yeah, it's a rough cube. It's pretty ugly, in fact. Yeah, but we see it's working. Okay, we see it's fine. We see that it's fine. I think we do. Yeah, sample plus 1. Yeah. Okay. Cool. 1, 2, 3. Oh, yeah, I'm thinking. 1, 2, 3, 4. 1, 2, 3. Yeah. Okay. 1, 2, 3, 4, 1, 2, 3, but then 1, 2, 3, 4. Like that. Okay, yeah. That is just the finest. Okay, there we go. So we have a sphere. The vertices and everything are fine. They look fine at least. Let's extrude that into 4D, shall we? So vertices and faces are correctly drawn. And then we can move on to drawing that in 4D. Just like that. I'm going to use the same code as the box for now. Just do simple shading, just to see how it looks like. Because I've never seen a sphere in fact. I have never seen it. And scale width, height, depth, well, that's not correct anymore. How should we do that? Radius, I believe. Radius, depth is, I believe, how that works. Make rotate. We're gonna have a couple rotations. Translate, of course. That's not needed anymore. That is needed. And we have basically all the same shit as for the box. Use everything again. Okay. That's a comment. That's a comment. That's a comment. And so is that. Okay. It's basically the same code as the box. The point is to intersect all the tetrahedra into triangles and quads and tetrahedra again, and just give those to OpenGL like nothing is new. Oof, sorry. Just like that. Buffer things. Normal. We do use the normals this time. It's not static. It's dynamic this time around. Temp.length is blah blah blah. Okay, projection matrix. Don't use that anymore. And use pmap for the projection. There. Draw elements, triangles, faces. Okay, it's not faces anymore. Box, tell me what is What is in there? Draw arrays. Triangle 0 10-point length. Alright. Triangle 0 temp dot length. Is that correct? Yes, it is, and it's arrays, not elements. Ooh, what is that? No. And this should be good. This should be good. Let's see. Let's see the 3D slice of our 4D sphere. Oh, it's laggy. Oh boy. Yeah, because it gives a lot of tetrahedra. So this is the problem right there. It's laggy as fuck because there's a lot of geometry being cut. But it's kind of cool seeing a cylinder and morphing in back and forth into a sphere. I think it's pretty neat. How do you feel about that? So yeah, it really shows how a sphere is indeed a sphere and a cylinder, right? It's a sphere extruded into a cylinder. Okay. What is your CLI? It's Cygwin. It's a good old Cygwin. In fact, it's I'm on Windows right now, and yeah, Cygwin. You can look it up, like so in chat. It's basically a Linux. It's a POSIX compliant environment in Windows, and as such, I think it's pretty cool. Okay, so there's way too much geometry going on, and in fact, I forgot to use the normals. There, so we should have good old-fashioned lighting this time, correctly, at least a little bit. Let's see, why not Linux? I'm just used to Windows. That's a fair question. Yeah, I just always used Windows, so I figured why not. Oh, that looks good. That looks really cool. Yeah, so you can really see how the rotation is affecting the facets. The facets are moving around. It's not just like plain old rotation. It's actually like different faces changing orientation and getting longer and longer, because like when it's fully into a cylinder, you can see that it's actually vertical rectangular stripes and not actually like little squares anymore. So yeah, there's our second 4D object. It's a 4D cylinder, as also called a sphere. Is 4D better on Windows than Linux? Not like that. I just meant that I'm more used to a Windows environment because that's what I've been using all my life. And because we are using the HAX programming language, 4D should be exactly as good on Windows and Linux because it's cross-platform. Hey, little HAX plug. Selfish plug. It's not my plug. I didn't make HAX. Hey. Okay, we're gonna use like a quarter of the samples. In fact, 1/16 of the samples, because I'm using only 8 now. It's gonna be a little bit more ugly, but it's gonna be much faster. Oh boy! Oh, that looks great. That looks great. I think it does. Doesn't it? Is that only me? Am I having a nerdgasm all on my own? Because I think it looks great. I'm gonna actually. I just love how the facets like interleave and they seem to like self-intersect as it grows into a full cylinder and back to a sphere. The edges, I meant, like the edges, like they cross each other. Oh yeah. 4D is a mathematical concept thought out hundreds of years before computers. Yeah, of course. Of course it is. Like extra dimensions is as old as linear algebra, and linear algebra is pretty damn old. Well, extra dimensions are at least as old as linear algebra. Older than that, in fact. But the concept of dimensions has been like rigorously defined in linear algebra first, I believe, if I'm correct. Good that 4D is cross-platform. Nice project. Thank you. I try my best. Yeah, so sphere. I'm gonna reverse the rotation to make it look even better. Because I'm cool like that. I care about my aesthetics of my 4D objects. Yeah, but then you see quickly the problem here. Because we only had like 32 squared vertices. And the thing is that every triangle gives 6 tetrahedra. No, every triangle gives 3 tetrahedra. And every tetrahedra can give up to 4 triangles, so it escalates pretty quickly. The number of objects on screen is very, very, very fast. Definitely looks badass, doesn't it? Okay, so the cylinder is going to rotate counter, like in the other way as the cube does, because I care about aesthetics, but I'm not that original, so I'm just going to reverse the signs of the rotations. Okay, yeah, that already looks better. Okay, I think we have a thumbnail. No. If you've noticed on the Twitch page, under the video I have a couple panels, and I like to show last time on stream we did. And unfortunately the panels, they don't let me play GIFs. So I kind of have to link it, and that's fine. But I'm definitely going to use that next, because holy shit, that was cool. 40 objects, yeah. Okay, so next thing we want is actually smooth out, actually use the normals. I'm going to compute the 3D normals of the sphere, and I'm going to use the 4D normals extrusion code that I've done at the beginning. Like, for anybody who wasn't here, this code here, geometry 4D, it has a function from 3D. Basically, you give it a 3D geometry with 3D faces and optionally 3D normals. And it does everything to make it 4D. Basically, it just extrudes the geometry along the 4th dimension, giving it the Duth. Duth is the name I gave to the 4D length, because I needed to name it something, right? So yeah, what this does is take the 3D geometry, take all the triangles, extrude them by this amount in the 4th dimension, which gives a 4D prism, which is like an actual prism. We do the drawings to explain to ear-disabled people. Yeah, I extensively draw on our good bro MS Paint over here. Hello. So yeah, how that works is if you want that, basically what I do is I have 3D geometry. So oops, for example, I have this cube, rectangle. Well, fuck off, rectangle. I say there. I have this. Come on. Okay, I have this rectangle. Oops. We are gonna do an analog, like from 2D to 3D, right? So this is my thing. It's a 2D object. I want to extrude it to 3D. So what I do is obviously take all the edges and extrude them. Take all the vertices, like for every edge, take the vertices, extrude them along the Z coordinate, and add an extra thing like that. Wink. And then do that again. And yeah, basically that's how that works. You just take, you loop over the edges, and for every vertex on each edge, what you do is you add an extra vertex that has the new Z coordinate, basically, like that. And then you are left with the 4 green vectors here are the like kind of transitional vectors, edges, and then the red ones are extruded vertices. So like these ones and these ones over here, like those have same xy but different z coordinate, is how that works. Yeah, but opposite z even. So this is okay, this is fine at all, but then in 2D, while you have edges, in 3D you need triangles. But then you know that if in 2D, if you take an edge and extrude it like that in that direction, I'm gonna draw again because I'm cool like that. You extrude it in that direction. then you know that if you take an edge and extrude it, you're gonna get a rectangle. Is it 4D rectangles? Yeah, I'm getting there. In fact, this is 2D to 3D. It's an analogy, right? This is only 2D to 3D for now, and we're gonna apply it from 3D to 4D afterwards once we know what's going on and we are familiar with it. So yeah, extrude in that direction, which is Z, in fact. Wink, wink, wink. And yeah, that's how that works. So if you take an edge and extrude it, you have a rectangle, a 2D rectangle. But then you need triangles. But that's fine because you already know that a rectangle is in fact 2 triangles. So you can have that pretty easily, no worries. Wink, wink. So that's how you take a 2D geometry and extrude it along the z-axis and turns all of that into triangles. It's pretty straightforward. You just do that for every face that you just created, basically. So that's another question that arises is, what do you do with normal vectors? Normal vectors like that are vectors that are orthogonal to quote-unquote faces. In 2 dimensions, faces are actually just edges. And so normal vectors look like that. They are orthogonal to faces, right? In the dimensionality that we care about. So then you might ask yourself, what do they become? Because those are 2D vertices. Vectors, I mean. 2D. Right? You're going to have to use your imagination to read my writing because I only have a mouse over here. Oh, jeez. It's not even cooperating. 2D. All right. 2 dimensions. But then this object is 3D and you need 2D normal vectors for every triangle. Well, we worked out earlier on the stream that in fact what you can do is if you have the blue normal vectors, new ones, nx, ny, and z, is you take basically the xy of the 2D ones and add a 0. That is because the normal vectors at the start they were already orthogonal to the axis of extrusion, and there's no reason they should stop. So take the same xy and put 0 in the last coordinate, which is also the coordinate of extrusion, so that it's orthogonal. Okay, Freddle. I'm not sure what those letters are. If there's a bunch of L's, then Freddle. Thanks for coming, and I hope you enjoyed, and have a good time. Bye. Okay, so that's what we do. Like, we have everything we need. So now we start over, but from 3D to 4D. So 3D to 4D is a little bit more complicated. What I do is just do it for one triangle. So our 3D thing is a cube, right? And we want to make it 4D. And first of all, we start with a 3D. Start with 3D like that. Boink and the boink. Okay. And then what you do is we define 3D objects using their boundary. It's a bunch of L's, okay. You define 3D objects using their boundary, right? So again, triangles, good old-fashioned triangles, no big deal, nothing new here. And I'm gonna isolate one single triangle because it's gonna be a lot of triangles if I don't. Okay, let's draw a triangle. Oops, oops again. Yeah, this is my triangle. It's a fat triangle. I like it. Okay, and we want to turn that into 4D like we did last time. So last time we took an edge, extruded it in the 3rd dimension, it did a rectangle. Okay, so this time it's exactly the same thing. We are just not very familiar with it, but we can actually do the same thing just in 3D. So in 3D, take this triangle, extrude it along the z-axis again, and see what gives. And we see what gives, and it gives a prism, which goes off screen. Another thing. Oops. Bam! Doesn't go off screen anymore. Shit. Okay. Yeah, it's a prism. It's a prism, and this prism. Oops. Yeah. Okay. This prism is pretty cool. Why? Because, as I said, in 4 dimensions, we cut things into tetrahedra, and a prism is actually 3 tetrahedra. If you don't believe me, then... But why? Why, bro? Why? I thought we were friends. Yeah, no, it's actually 3 tetrahedra. You can do the math. It's tedious and boring, but you can do them if you want. And the point of it is that when you do a prism like that, just like that, that's our prism in 3 dimensions. You can actually cut 3 tetrahedra into them. Oh, that's... Oops. Okay. Then big fat lines. That's one. That's one right here. 1, 2, 3, 4. Just like that. There's another one. Yeah, it's kind of weird, but I guess it's doable. Like that. There's one here. There's another one here, and it's in some way you can make it out. And this is how you extrude triangles into prisms. But then here we only did it in 3 dimensions. But the actual trick is that this direction this direction right here. It's not the z-axis. It's not x or y, but it's actually w. Beautiful w. Yeah, it's actually the w direction. And here in this drawing, what I did was I basically forgot about z. Because if I didn't, then it would be very complicated for us humans to understand what's going on. Because we are only able to perceive 3 dimensions at a time. So just like that. This would be my current axis system. So this would be x and y and w. Oops. X, Y, W. There you go. And then you ask, but wait, where is Z? Well, it's because we are humans. As I said, we only see 3D, but if you really want, I could draw Z. It would look something like this. Something that doesn't make any sense. So yeah, if you really wanted, then there you go. Have the whole of 4D axis system in one picture on one 2D screen, but it doesn't make sense. How are you representing rotations in 4 dimensions? Exactly the same way that you do in 3 dimensions, minus quaternions, if that was your question. So if you go back to the notepad, good old bro, there, you see that to display my cylinder, I have this. UMAT, I create a matrix 5, which is exactly what you think. It's a 5 times 5 matrix. And then I do a couple more matrices, make rotation, blah, 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 blah. So in 3D, I mean, you are probably familiar with quaternions. Quaternions are 4-dimensional objects that have the interesting property of being able to describe 3D rotations without something that is called gimbal lock, that basically gets in the way of you representing rotations correctly. In 4 dimensions, there is nothing like that. There is a mathematical theorem that says that an algebra has to be of dimension, an algebra has to have a power of 2 as a dimension. That's a theorem. I love me some quaternions, I bet you do. An algebra has to have a power of 2 as a dimension. What does, well, English, hello, as a dimension. What does that mean? It means that in order for a field, okay, topology time, if you don't know what's going on, it's fine, don't worry. A topology such as R, plus and times, well, basically a field, for a field to be an algebra, it has to be a power of 2 as a dimension. So R plus and times is dimension 1, that is 2 to the 0, so it's okay. The field of complex numbers plus and times is also dimension 2. So that's 2 to the 1. Quaternions, which are h, plus n times, plus n times, dimension 4, so that's 2 to the 2. And there's something called octonions, octonions, like it's q, no, it's o, I believe, in fact. Plus times is dimension 8, and that's 2 to the 3. I know there are octonions, 1 real component and 7 imaginaries. I have no idea what it's used for. It's not used for anything, in fact, because one property of algebras is that as you go down the ladder of dimensions, you lose properties, in fact. You lose the property. What is it? Well, it's probably something stupid, but I forget what you lose when you go from real to complex. Yeah. When you go from complex to quaternions, you lose commutativity. And when you go from quaternions to octonions, you lose associativity. And if you lose associativity, then you cannot represent rotations anymore, because rotations are associative, in fact. So, not commutative, it simply means that A times B is not B times A anymore. And that's fine. Quaternions are not associative, but then again, neither are rotations, so that's no worries. Not associative, however, it's more complicated, because A times B times C is not always A times B times C, which means that the order matters. But in rotations, the order is not supposed to matter, so you can't actually use you can't actually use octonions, which, by the way, are like that. That's quaternions, that's complex numbers, that's real numbers, just like that. Then again, you would be able to do like whatever algebra, like of dimension 16, but you would like basically lose every property that would make an algebra even remotely interesting. So yeah, we'll just stay here. And yeah, octonions are not associative, so as such, you can't use it to describe rotations. But this would be what would be needed to describe 4D rotations properly. So RIP. Instead, we just use good old-fashioned matrices. 5 times 5 matrix. This also means, alright, so it also means that gimbal lock cannot be avoided in 4 dimensions. So if you're not careful with the order of your rotation, you can have some pretty weird shit going on because of gimbal lock. So you gotta look out for that. So yeah, rotations, you don't have a choice, matrix 5. 5 by 5 matrix, exactly the equivalent of the 4 times 4 homogeneous coordinates matrix that you know. Where will 3D vectors lie? Is it just 3 one-dimensional components? In 3D, well, in 4D space, everything that is quote-unquote less than 4D is included in it. So you could just say that 3D vectors are 4D vectors with a 0 coordinate along the W axis, right? You would just do something like that. Paint my dude. Yeah, just like 2D vectors lying in 3D space could be represented as normal 3D vectors with a z equals 0 coordinate. You could just say that 3D vectors lie in 4D space with W equals 0, basically. So yeah, it's just the same. It's just a generalization of things we already know, basically. That's X, that's Y, that's Z. Yeah. And basically everything in that plane, like the plane Z equals 0, you could draw 2D graphics in it, basically. And it would be just like, oh, but it's 2D, but it lies in 3D space. And like our world, all of this, like this is the same thing. Like this our whole world could be like a 3D subspace of a 4D space, right? Which in turn is called a hyperplane. Like this could just be it. This could be our lives. And yeah, and I did not draw that correctly at all, but that's fine. Yeah, this could just be W equals 0. Our whole life could just be the 3D part of a 4D space, like W equals 0. And in fact, that's theorized in a theoretical physics. It is one theory among many others that electrons move in 4D space, and that's why they just seem to pop up and randomly appear and disappear out of thin air in space around their atom. And so yeah, that's one way of looking at it. If that answers your question. Does it answer your question? Okay, so we did the good old 3D sphere. Let's look at it again. I sure like it. I dig it, if I will. And then we want to calculate the 4D normals, which we are, in fact, going to do using the 3D normals. We're just gonna basically have this sphere. You calculate the 3D normals of each vertex. We're gonna have a per vertex thing. After that, we are gonna extrapolate them into 4D, into a cylinder, which our code does already, in fact. The geometry 4D from 3D function, which is here. You can see here a vertex normal. It does what I said. It takes the same x, y, z and adds an extra 0 because normals are orthogonal to the direction of extrusion. It does this twice because we have 2 copies of every vertex, in fact. And so it should work just like that, right? So cells have their own normal. And what is interesting is that we have, strictly for interpolation purposes, we have a per vertex 4D normal vector. But then we also have a per face normal vector. And this is calculated like so in the compute normals function using what I've presented as the 4D cross product. It's literally the 4D equivalent of the 3D cross product, except that it takes 3 arguments instead of 2. It would make sense, right? Extra dimension, extra argument. Is that shady enough? No? Should I go even shadier? Alright, so we're gonna try that out. In the cylinder, we're gonna have normals. In fact, we're gonna have exactly that. Boink. It's gonna be mostly the same. And in fact, the normals of a sphere is exactly the positions, so we don't even need that. Instead, what we do is give geometry.form3D vertices twice, because as I said, positions are actually normal vectors as well. So it's a kind of cool trick. Quaternions took me long enough to wrap my head around. I'm starting to understand this. Oh yeah, in my opinion, this is much more intuitive than quaternions, because quaternions are for the objects that you give extra meaning, right? But here it's just literally points with 4 coordinates, nothing more. It's nothing more than that. It's just the dumb and immediate and trivial generalization of what we already know in the form of 3D vectors. Literally the same thing. The only thing complicated about this is giving meaning to everything because it doesn't exist, right? We can't experience it in real life. So it's, in that sense, it's harder than 3D. But apart from that, it's literally exactly the same thing going on. Okay, so we do our good old normal bros over here. Geometry 3D has a vertex normals array. Vertex normals. English, accents, pronunciation, all of that shit. Okay, here comes the hard part. What do I do with vertex normals? How are they used? Because they need to... I don't know, man. I don't know. It makes me think that I should probably use, have an attribute. That would be something like that. Attribute vec for A position 4D, something like that, and then use the vec for A normal 4D, sorry. This is gonna get interpolated, but then again, we are not passing the actual vertices to OpenGL. We are passing the intersect tetrahedron, right? So because of that, it gets really, really strange. So what do you guys think? All 5 people watching right now, welcome and hello and thank you, by the way. And so that's what I'm wondering here. Shout out to Alexander, my bro, who's in chat, I've been told. If he even still is here. So yeah, we do that, and yeah, we have per vertex normals, but problem is, we're not giving vertices. We're not giving the base vertices to our 3D renderer. We are giving the intersections of the tetrahedron described by the vertices. So what I'm thinking is, if you look at the intersector code for intersect tetra, we are actually intersecting along edges. So what I'm thinking is, I think I'm sticking with 2D. Yeah, that's it's much easier, if you will. Yeah, well, you can have pretty sick tricks with 2D also, but I'm more interested in seeing what's beyond, you know, what's beyond what's possible to see in real life as well. Like something that I said in the prior stream is, somebody was asking me, why do you do 4D at all? Like, what's the point? And then I say, well, we cannot. 4D is hard to understand because when the computer displays it to us, we have trouble like being able to tell if it's right or wrong because we don't know what it's supposed to look like. But then I'm saying, hey, we would be able to tell what it's supposed to look like thanks to computers. So instead of trying and verifying what 4D should look like, just trust the computer to tell us what it does look like, because it is able to render it and we are not. So yeah, I think based on that principle, I think this is why I do this and why it's so interesting. And don't tell me that it's not worth it when you see like the super cool cylinder 4D sphere and cylinder mashup, like mixture of math and shit going on like that, with all the faces doing crazy shit. Come on, don't tell me, don't even tell me. Don't even begin to pretend that this is not worth it. This right here. Yeah. Okay, so yeah, linear interpolation is what I'm thinking. Because our 4D vertices stop being used right here, intersect tetra, they stop being used right here. It's very interesting, don't get me wrong. Oh no, that's not what I meant. But I'm just stating my motivations, is all. Like, I'm not saying you don't think of it highly enough or anything. I'm just stating my motivations and why I'm not sticking with 2D or even 3D. Because I don't know shit about like the very complicated, super advanced math shit that goes on in the big 3D engines, right? Like you could say 3D is complicated enough, but then for like apart from being complicated on its own, 4D is not only complicated; it's also a novelty. Well, not in concept, but in implementation. There are lots of 4D hypercubes, thing like that going on, but it's all projection, and in my sense, it's not very interesting because it's just flattening 4D into 3D. What I'm doing here is also what Migakure does. Migakure is a 4D game that you may have heard of. If you haven't, check it out. It's very cool, but it never came out, so that's also why I started doing that. Yeah, that's why I do it, because it's so interesting and such a novelty. And also because I like inflicting pain upon myself by thinking about unnecessarily difficult math problems. So yeah, I'm splitting also. Okay, so yeah, this is what we do. And yeah, so on the subject of vertex normals, we need to be able to give meaning to those. And if we go in our render pipeline, which right now is duplicated, but that's okay. Matrix, blah, blah, blah. Okay, so we loop over the 4D cells, build the tetrahedron using the model matrix. The view matrix is PMAT, is here. So it's actually independent because the the view matrix is actually applied in 3D space on 3D points, but the model matrix is applied in 4D space to 4D points. So the model, you can't speak of a model view matrix anymore because those are different things entirely. The model matrix is a 5x5 and the view matrix is a 4x4 because there has been a change of basis in the meantime. So yeah, model matrix. Then we calculate the actual tetrahedron in space thanks to that model matrix. Then we intersect, and that's where V1, V2, V3, and V4 stop being used. They're not used anymore because any reference to V1, 2, 3, 4 is those, in fact. And that's when it gets complicated because we have the normals, the 4D normals, we have them. We have calculated them, but then it's only pertaining to those. But they stop being used right there. So what I'm thinking is intersect tetra should actually give an array of parameters, right? Instead of returning flat out points, like it does, right? It calculates the line space intersection. Basically, how this works is roughly, not in detail. How this works, in order to intersect the tetrahedron and space, it's enough. You can prove mathematically that it is enough to just calculate the intersection between the 3D space and the edges, and so that gives you points, right? So what I'm doing right now is pushing the points, but I'm thinking that what I actually need to do is not return the points, but instead return a factor of linear interpolation, because we are interested in edges, and intersecting edges is equivalent to finding the t parameter, so that linear interpolation between v1 and v2 of t gives the correct points. And that's not only useful for position, but we can interpolate any value with it. If we have a color value, then the color value of the intersection is also a linear interpolation of factor t, and etc., right? So in order to do that, I could build a certain struct, typedef struct, which I'm going to do. In fact, typedef intersection result. Typedef intersection result is going to be what? What's it going to be? It's going to be v1, v2 float. Yeah, no, yes, no, maybe. Yeah, v1, v2 is float. V1 is basically all 6 edges. Basically all 6 edges. So in case that's not very clear, again, what I'm doing is instead of returning points of intersections between the tetrahedron and the space, which again are going to be points of intersection between edges and the space, it's equivalent. What I'm going to do is return parameters for linear interpolation, and that will allow us not only to interpolate position, which is what we did basically, but it's going to allow us to interpolate any property that is defined on a per vertex basis, such as normal vector, color, etc. And in fact, it's already what I do. It's here. This t parameter is I just do return t basically. Is what I do. Line space intersect returns. I'm gonna have to document that. Returns the amounts of linear interpolation between v1 and v2. That gives the intersection. Oops. the intersection between the hyperplane and the edge and the line. There. So yeah, we got it. Instead, we don't do that. We do that, just like that. And this formula is very easy and can be worked out by plugging the definition of a line into the definition of a hyperplane. No big deal. And t is the amount that we want. T goes from V1 to V2. Linear interpolation from V1 to V2. Be extra accurate. Okay, so this gives T then. And what you want is either float. Okay, this needs to be eventually discarded because not all edges intersect the hyperplane at once. In fact, a maximum of 4 edges can intersect the plane at once, out of 6. This is because, well, it's because math, trust me on that. Again. And yeah, so I want to be able to tell if there is interpolation, if there is a crossing at all. And I'm thinking, right? I'm thinking that a negative value should be enough to say that there is no there's no crossing, because in linear interpolation only makes sense in our case if it's between 0 and 1 included, not over 1, not below 0. So if we just say minus anything, it should register as no intersection. Okay, so intersection result is that. It is that indeed. So intersect tetra, instead of array of vector 4, that's gonna do intersection result. That's gonna return that, and R is gonna be exactly that. In fact, intersection result. Oops, there. R is intersection results, and it's gonna be, what's it gonna be? Well, by default, it's gonna be like, I think you can do that in Hex, if I'm not mistaken. I'm gonna look that up very quick. Hex default, well, type def default value. Okay, it's default values for optional variables in type defs. Am I able to do that? Don't seem to. Uh-oh. Type def params as optional with def. But that's the old language. No. If you have any question on what's going on, feel free to ask while I look that up. Sounds very interesting for all of you all. Okay. Type def is just an alias for type, so it probably means a structure type. The thing is, it's mostly a compile time definition. It can only file within your own type. Default values makes no sense. RIP. We could just use a class. Okay, so there's no default value. Well, sad. I'm actually sad. Well, I guess we could just do like lazy initialization, but I'm not sure, and I don't want to spend time doing that. So there's no default value, RIP. So I'm just gonna initialize everything to, well, everything is initialized to 0 by default because float is a primitive type. But we can work that out. We can, in fact, work that out. What we're gonna do is do it the ugly way and initialize everything to -1 ourselves, in fact. Minus like point. It's annoying that I have to specify that it's a float because int does not unify to float in Hex. Like, it's kind of like camel. It's very sensitive about its type checking. So we have to like include the point to make sure that it's a float and not an int. Okay, so S1 is sign of hyperplane. Blah 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 blah. If math is, okay, so here is first case. If the tetrahedron is all on the same side of the hyperplane, return R. There's no intersection whatsoever. Yeah. And in fact, we can just have an extra field that tells us how many intersections there are. And so we don't have to count every time. Intersections starts with 0, of course. Okay. Return R. Then second case, if one or more vertices are inside the hyperplane, the number alone determines the shape of the intersection. Okay, so if S1 is 0, it means that V1 is in fact inside the hyperplane. So as such, R dot V1 V2 is 0, like that. Because yes, linear interpolation between V1 and V2 with a factor of 0 returns V1, in fact. So that works. And also increase R dot intersections by 1, of course. No, not like that. Okay. That's going to be extra annoying though, but yeah. Just like that. If S2 dot 0, if S2 is 0, then of course make it so that we don't overwrite the previous one. Equals 0 again, and then intersection extra. Oops. And then V3, V4. Yeah, and then intersections. Oh boy. Aren't you glad I speak English? Could you imagine if I couldn't write? Okay. And then S4. S4. I don't know. V1, V4, I guess, is 1. And intersections, again. Okay. Here's this thing, though. Okay, it doesn't matter because we know that these edges are not going to intersect anymore. Third case, the hard one, where the intersection is a triangle or quad, we intersect all edges with the hyperplane to find points. We know that the line cuts the hyperplane. Okay, so if this is true, we're not going to overwrite those, so it doesn't matter. I could take any edge that includes 1, I could take any edge that includes 2, I could take any edge that includes 3, I could take any edge that includes 4. I just have to make sure to not overwrite those, like, among each other, because those are never going to be met with those, so it's fine. Yeah, R.push is actually not what's going down. R.v1, v2, because yes, it is what is going on. So it's going to be v1, v3. Oops. Okay, that's going to be v1, v4. And yeah, we check every possible edge in the tetrahedron. Basically, oh, that's, what was it? V2, V3. Oh, sorry. Little hiccups. Literally. Nothing wrong going on this side of the stream. I dropped 0 frames. What? What is this real life? How? Is this real life? I'm asking. Guys, tell me. Is this real life? It's not the real life. It can't be because 4D things, what? What are those things? And V3, V4. Okay, and now actually increase the intersection. Ugh. Blah. Annoying, slightly. Okay, here's what we do. Yeah, I think we can regexp our way out of there. No, let's not. Let's not do that. Intersections. Plus. Just like that. Instead, we're going to just do that. That'll be enough. Oops. Yeah, that's good enough, I'd say. There we go. And then, bam. Whoops. Not like that. Well, let's do it even better. Just like that. Bam, bam, and bam, and bam. There we go. Okay, so as far as I know, I did a column instead of semicolon. Damn it! I still find one way to fuck it up all the time. Okay. Okay, so that should be enough then. Return R. And again, line space intersect returns the amount of linear interpolation from V1 to V2. So we can use that then to interpolate anything and not just position. And that's very interesting, if you will. So for now, we're gonna get rid of sphere-render. We're not gonna render it. We're gonna make that work with good old Boxaruni over here. Good old Boxaruni. Sphere-render, you can go. Cell, you can go. Intersector, you stay. Vector 4, you go. Geometry 4D, yeah, we don't need you. Main, yeah, we'll keep you. Okay, let's do it. Okay. Intersector, again. Intersect tetra is gonna return an intersection result. So first of all, import alphabetical order. Always, oops, intersector dot intersection result. There. Is that what's going on? Yes. Cool. And 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Counting. Yes. Okay. Box. Box. We're gonna have to change that. It's not map anymore. That's not real at all. Boink. Okay. So what we do for now, all we do is we just basically interpolate position. Is all we do. We're gonna have a function var inter results, and R. We're gonna fill R with everything that is necessary, basically. So yeah. How do we do that? R. I wanna clear R, in fact, but there. So inter result. So instead of R.length, it's gonna be inter result dot intersections. Is gonna be the number of vertices. We order vertices to have minimum successive angle difference. Yeah. Okay. That's gonna be okay. All right. If I push all my vertices to R, it's gonna be much easier. Yeah. It's just so that we don't have to query every time. Well, in fact, I don't really care about the number of intersections then. All right. I'm gonna write the code, and I'm gonna remove what's in extra later. We just do once at a time. Okay, so if inter result dot v1 v2 numpad v1 v2 is over 0, r dot push okay, I need a linear interpolation. I believe vector 4 has that. I do believe. Can you tell me that? Linear interpolation? lerp? No. Length squared, direction only. Add angle between, clone, copy from, cross product, decrement distance dot equals increment by, equals negate, normalize, lerp. Okay, I'm gonna add a lerp really quick. Lerp, lerpy doop, inline public function, lerp. Is it going to be a.lerp? Yeah, fine. Okay. All right. It lerps to b by an amount t. Sounds about right. It stands a new vector 4. Okay. So it returns this plus, well, returns add. Okay, wait. Multiply scatter. I don't remember what's called. I don't remember what I wrote as functions. Dot distance decrement by, cross product copy from, clone add. Yeah, add. I remember that. Negate, normalize, scale by. Not in place. I would like it to not be in place. Shit. I'm gonna rewrite a reentrant API for next time because this is painful. Dot distance decrement by. I want add. Add is not in place. Cool. Scale by. I want to not be in place also, but decrement by distance dot equals multiply scatter. Okay, so basically we want like a b minus a times. Oh yeah, we could just do that. B times subtract a times scale by t plus, well, dot add this. Huh. Alright, that should do. And A is this also. Yeah, because if t is 0, then b minus a times 0 plus a, so it's a. And if t is 1, b minus a plus a is b. So yeah, that sounds right. Is subtract, okay, subtract is reentrant, and it's not in place. Cool. Okay, so the lerp should work, and it could be inline, yeah. B dot subtract this dot scale by t dot add this. Yeah, sounds about right. We have a lerp now. So r dot push v1 dot lerp v2 by into result dot v1 v2, and copy that a bunch of times, and that everything we love and more. And I'm gonna include the tab. Poing poing. Whoops. 6 times, in fact. 1, 2, 3, 4, 5, 6. Because it's gonna be v1, v2, v1, v3, v1, v4, v2, v3, v2, v4, and v3, v4. Okay. So again, lerp along every edge if need be. So lerp to v2, lerp to v3, lerp to v4, lerp to v3, 3 I said, v4 and v4 again. Different starting vertices, v1, 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 v2, stop, v2 and v3, and different rates, v1, v2, v1, v3, v1, v4, v2, v3, stop, v2, v4, and v3, v4. Okay. Okay, I think we're good to go, except that I want to empty R every time for p in R. Oops. For p in 0, r dot length, r dot pop. There's no good way to empty an array in Hex, which is sad. But I believe that there was a study that said that this is faster up until 128 elements, and then the JavaScript like r.slice0 is faster afterwards. And this is faster, I believe. For doesn't matter, in 0 r.length, r.pop. Okay, this should empty R, then push it to R. Alright. This should be equivalent. Do it. Hopefully you don't compile Sphere because we're not using it. Okay, it's vector 4. Vector 4 has no field subtract. Oh yeah, it's sub. Sub for sub. Ha. Yeah, it's sub. Vector 4 should be vector 3. Oh yeah, shit. I'm pushing vector 4, but I should actually use like main dot intersector dot switch base. Is what I should do. Ah, my god. Okay, regexp time. I'm not going through this. Okay, regexp. Yeah, you can't see the regexp. Sorry, I have a little window of find and replace. So sorry about that. R.push parenthesis anything. Okay, no, never mind. I don't remember my regexps. Never mind that. I'm gonna do that very boringly. Main dot intersector dot switch base. Yeah, what's going on is that we are pushing 40 vertices, but you will have noticed that R is actually an array of vector 3. So you say, hey, what's the deal? What goes on here? And in fact, what's going on is that we are indeed pushing 40 vertices. However, their expression is in the basis of the intersector. What that means is that the intersector is the 3D space, as I've said. And as with any 3D space, it's contained in our 4D space. Of course, it's part of our 4D space. So this is why. So because of this fact, this result has no field map. Yeah, sphere-inder, just don't use sphere-inder. Don't use it. No. Sphere-inder, hello. Okay. So yeah, as I said, because our 3D space lies in 4D space, then that means for every point in 3D space, there are two possible representations. The first one, local variable r used without being initialized. Oh yeah. Hoyer. Is new array. Wink. There. Shit. Yeah, so because every point in the 3D hyperplane is also contained in the 4D space, whoa, that's not quite working. It is not quite working. What is that? Do you see this? Yes, you do. Okay. That's not quite working. Okay, there's something going obviously very, very wrong over here. Into results, I'm gonna trust that the intersector function is fine, and first of all, see if I didn't fuck up anything here. v1.lerb v2, v1.lerb v3, v1.lerb v4, v2.lerb v3, v2.lerb v4, v3.lerb v4. Okay, so that's fine. First of all, if it's positive, okay. If it's positive or 0, in fact. And then we push it. Okay, we push it in the same order than we did last time. So it should be fine. In fact, as a check, what I'm going to do is trace r.length and see what that gives. And if we get anything other than 3 and 4, then that means we fucked it up. Okay, we do get other things than 3 and 4. We also get 0, but that's fine. 0, we are not pushing anything, so it's okay. Okay, we only get 3, 4, and 0, so that's fine. I was more worried about getting 5 or 6, but that's fine. Cool. Okay, so what does it mean then? If interresolve v1, v2, v1, v3, v1, v4, v2, v3, v2, v4, v3, v4. Okay. v1, v2, v2, v3, v1, v4, v2, v3, v2, v4, v3, v4. And same thing here. Okay, so that means I fucked up something here then. And that what that means. Line space intersect u.scale by t.add v1. Yeah, that's v2 minus v1 is what that means. Exactly how malherb does it. v2 minus v1 scale by t add v1 is basically what that is. Yeah. Okay, so it returns t instead. And u is normalized, by the way. So it does mean that t is 0 for v1 and 2 for... Oh, wait. Oh, no, it doesn't. Oh, no, it doesn't. If t is 1... Oh, no, it doesn't mean that. Oh, shit. Okay, this is the error right here. That's the error, in fact. What does that mean? U is the directional vector, but it's not scaled properly. Okay. I know. I think I know. I believe I know. Divided by u dot normal. Ah, do I know? I don't. God damn it. Okay, this is times. No, this divided by u dot the norm of this. I think t is off scale. In fact, I'm pretty sure it is because because in which conditions, if t is 0, like there's no question, then it's indeed v1. But then, under which condition on t do we get V2 out of that? Because U is normalized. See, U is normalized over here. And because of this, I think T needs to be equal to the distance between V2 and V1 and not 1. So as such, we do that. V1 dot distance V2. I think I've done that. Distance. Remember? Yeah, distance. Okay. That's a shitty workaround, but that'll do for now. So how is this? Or maybe it's divided, in fact. Cannot access static field. Okay, it's a static field. V1, V2. A vector 4. Hey. I know how to do axe. I know how to do the axe thing. Don't you worry. Okay, it's even worse. That means we have to divide it and not multiply. Which would make sense, in fact. Which would indeed make sense. Okay, and then we have it. Back at what we had. Okay, pretty cool, pretty cool. So we don't need to normalize U. I think. I don't think we have to remove. Well, yeah. If we don't normalize U, it should be fine. Like, remove that, remove this, and don't normalize U. Because if we normalize U, it's the same thing as multiplying T by V1 minus V2. And that's why we had to divide it again. Because normalizing U is dividing U by something, and because U is at the bottom of the divide sign, then it's like, instead of dividing this, we multiply this. And this, we divide again. So it's equivalent to not doing that, and also not doing that. And it should cancel out, if I know my math correctly. Famous last words. Okay. I know my math correctly, good. Happy day, okay. Whew. Oh, yeah, so we got that working. And that is thing. Okay, so our intersector works great now. It gives linear interpolations between stuff. Woo! Okay, so ISS, I confirm that we do not need to track how many intersections there has been. Indeed, we don't. So I'm gonna remove that because it adds quite a lot of code, in fact, and a lot of clutter. We don't want no clutter in there. Okay, so is everybody hanging out so far? How do you guys feel? Give me input. Are you impressed yet? It's very interesting. Yeah, I know it is. While I do that, while I remove some unnecessary code, yeah, you guys can do some unnecessary small talk. I'll be appreciated. Y'all. Oops. Okay, when that's done, we have all we need to start interpolating normals. That's gonna be hype, because then we have smooth spheres, smooth 4D spheres. Yo, how does that sound? Well, first of all, we can interpolate color because it's much easier. Because we have to use normals. Like normal vectors are going to be 4D, and our shader is going to be 3D. So that's going to be a little bit. It's going to be a little bit on the hard side of things. English, blah blah. So yeah, we're gonna just interpolate something easy, like a color is fine. We're gonna keep our a cheap lighting method in the shader because it's gonna be much easier to not care about it. Okay, so this is this gives us the lerp amount. And by the way, at the end of the day, I want this whole thing here, like the whole intersection. I want this to be done by a geometry shader in the end. And this is why having intersection in the form of the factor of a linear interpolation, this is interesting for me because then I will be able to interpolate all sorts of crazy shit like normal vectors, color, material, like some visual type deal, something like that. So okay, so we have a lerp. Oh, first of all, because I've removed the number of intersections, I'm just gonna check that it still works. I don't think I've used it anywhere, but you never know. Okay, still works. Good. Alright, so I'm gonna remove those vertices as well. I'm gonna leave that. We don't need those. Alright. Alright. That's fine. What more do we need? Okay, I'm gonna adapt this. Well, yeah, I'll adapt this cylinder as well. I'm just gonna adapt this cylinder as well. It's basically copying that and pasting it on whatever is in its place. Ghost Surrender. Sounds like a Pokemon. Surrender, use Thunderbolt. Use Mindfuck. Boink. Okay. R you need to actually exist. New array. Boink. Right. This should be enough. I believe it's enough. I do believe. Oh, I have to include it. Include the type for intersection result. Intersection result. Boink. Alright, do it. I didn't add it to main. Right, it should compile if it works anyway. Yeah, okay. Main. I want me surrender, bro. Please. Please give me the thing. Alright, it's all working. Pretty cool. For those of you who hasn't seen it, meet a sphereinder. What is a sphereinder, you ask? Well, a sphereinder is midway. Well, it's not midway. It's the 4D equivalent of a cylinder. When a cylinder is a circle extruded along its height, a sphereinder, as I like to call it, is a sphere extruded along its height in 4 dimensions. So that's what you get. This is being rendered by a method called hyperplane slicing, which is a little more than a simple projection, but I think it looks really fucking cool, if you ask me. So you can see how, in some ways, in 3D, depending on the angle you look at it, you could see a cylinder as a circle or a rectangle. And then in 4D, I mean, depending on how you look at it, a sphereinder can look like a sphere or a cylinder. And this is what this shows right here. So yeah, I dig it. So now we have our framework for basing everything on linear interpolations. Basically, it's what that is. Like, this is all being done by linear interpolation. Also, all this code is the same. In fact, I believe those are all the same. So I'm gonna write off stream. I'm gonna write a little object class, which is gonna have this very routine, this render function, because it's the same for sphereinder and box. I'm just copying shit around. I believe it's the same, at least. Yeah, apart for a couple comments. Yeah, and it's the same thing. So I'm gonna write an object class after that. In the meantime, we have interpolation to do. So intersector, we are done making it return linear interpolation values, rates, if you will, rates values of rates. Yeah. So what I'm gonna do is, first of all, I forgot to put the link to the stream on Twitter, so I'm gonna do that. Oh, did I forget? No, I didn't. I actually did do that. All right, never mind. I didn't forget nothing. Okay, so what we do is, let's try and interpolate something funny, like the colors, for example. I'm gonna give to every sample a color, which is basically gonna be position. In fact, I could. Oh well, yeah. I could give it I'll give it a function based on phi and theta. How does that sound? And then we're gonna interpolate, and then we're gonna see how everything morphs and moves in 4D when you throw color in the mix. This should be pretty cool. So what we do is literally the same thing as vertices. Literally the same variables, but instead it's colors. There. Get colors. Get colors, bro. It's gonna be vector 3 as well. If vertices is not vertices, is colors, then colors, because new array. Here's the spheres, vertices, color. Have I said colors enough already? Theta step and phi step. Okay, no. No, no, no. No, 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 no. What can I use? I don't want to. Oh, Dazzleime has HSV functions. Hack Lime HSV. I don't believe it has. No. Okay. Oh yeah, it does. Color. Oh no. ARJB BGRA RGBA. RIP. RIP. F for respect. Okay, math. It does have a color matrix, but it's not HSV. It's also not HSV, so RIP. Okay, we'll just do the stupid way. Actually, I'm thinking it would be easier to do the faces, but we are just going through the vertices anyway. Theta step is J, phi step is I, and then do not that. Do not that. What do I do? What do I do? Okay, we're gonna map red, blue, and green. Red to I, blue to J, green to J, and blue square root of sum of squares. How does that sound? Length of I and J over samples. How does that sound? What am I doing? Colors dot push new vector 3. J is Y, I is X basically. I over samples, J over samples, and math dot square root of I times I plus J times J over samples. There we go. This should be good, I believe. Colors dot push, yeah. As long as we have as many colors as vertices, this should be fine. Well, it's over math dot square root of 2 times samples, in fact, but that's fine. So it stays between 1 and 0, 0 and 1 in that order. Okay. Alright, so we are going to interpolate this as well. How about that? Normals, and on top of that we have colors. Wait, didn't we have normals already? No, it's just to store shit. Okay, we have colors 3D, which sounds weird, but it's fine. Okay, so basically then it is another one of these. Another one, except now it's C1 var C1. So yeah, it's basically another round of all of that. Another round of all of that. Eventually I'm gonna have a loop, go through vertex attributes and do that on its own. So alright, so instead of geometry.vertices, oh wait, there's more. Oh man, there's more. I defined colors, one color per 3D vertex, not 4D vertex. Ooh, that's, well, how do I do that? What do I give? What do I give my colors? Well, okay, I guess we just, I don't know, actually. I don't actually know. What sense do we give? What meaning do we give to the colors? Like, do we give the same color to two extrapolated vertices that come from the same vertex? That sounds like a reasonable idea, doesn't it? I wonder. I really wonder. I guess we can. Yeah, that should be fine. Yeah, because I don't know if it's still gonna work with normals, right? Well, it's what we're doing. We are doing exactly that with normals, so there's no reason it shouldn't be logical or meaningful to do that with colors as well. So because we know that extrusion is actually copying the same vertex with a different depth, then we know that duplicating the colors array is exactly the same thing. And we also know that duplicating the normals array is exactly the same thing, in fact, because we are only keeping, we are just using x, y, z, 0. But yeah, food for thought. It's not gonna remain true because of reasons I'm gonna attend later in another stream, in fact. Okay, vertices colors. So those are our colors. So we're gonna just do a modulus. We're gonna cheat basically, like colors 3D. We're gonna cheat. Okay, let's do a cheating. I am gonna do a cheating, and I'm gonna do, in fact, this cheating will be done via modulus. Modulus of the color array. Modulus length of the color array. Colors number equals colors.length, just like that. A is going to be colors c.a modulus colors number. And not umat by any means. Do not multiply umat dot modulus colors number. And it should be exactly fine, in fact. Because remember, I am adding the color, I am adding the extruded vertices at the end of the vertices array. Like, first is the one round of all negative depth vertices, and then is one round of all positive depth vertices. So, because that's going to be exactly twice as many many colors, then doing a modulus is just gonna work. Trust me on this. Trust me when I say is what I meant. Okay, and now we can lerp. Let's do the lerping. Do the lerping. Okay, so when we do push triangles, we're gonna push the colors. Wink. Colors array of float, I believe. So push vertex, and then push vertex on the normals, and then well, I don't know. I don't know about that, in fact. No, that's not, we can't do it that way. It's not that easy, I guess. Yeah, we can. Yeah, we can. Current colors is, in fact, the multi, is there a multi-index thing? No. Current colors is exactly like C1, C2, C3, C4. Just like that. And then we give current colors that, and we just push it, and it's okay. Yeah, okay, that sounds about right. I'll do exactly that, in fact. Because that's very ugly. Yeah, okay, boohoo. But I'm gonna clean that up in between streams because it's not too interesting to have. I'm more interested into the end result than to like make it work first and then only optimize it, right? So colors, array of float, for real this time. And in fact, current colors is gonna be the equivalent of our array over here. Current colors, array of vector 3 equals nothing. Does not equal anything. Current colors, we are setting it every time, so we don't need to give it an initial value. And as such, colors, we can push shit to it. because current colors is defined. So what we do is colors dot. Oh, hang on, that's wrong. Current colors is not that. Current colors. Oh my God, English is gonna be set the same way we set P. It's gonna be a lerp between whatever color is needed. So yeah, current. Okay, colors dot push. We're gonna do C1 equals current colors A. C2 equals current colors B. C3 equals current colors C. There, because we are pushing a triangle again. And then what we do is push vertex C1 colors 2, 3. Okay, 2 and 3. Hey, stop. Okay. So we are pushing vertices, normals, and then colors. Eventually, I'm gonna have a loop that does that efficiently in the end for every vertex attribute, basically. Or don't have a loop, unroll everything, and it's gonna be much more efficient anyway. Okay, so C1, C2, etc. Okay, so now I have to have an extra thing over here. Current. Okay, so I do need again to do the initialization because I'm pushing stuff to it. Okay, we know that R and colors have the same length, so as such we can just do that. All vertex, vertex attribute arrays have the same length. For further reference. And then current colors dot push, exactly that. But instead of v1, it's c1 dot lerp. c2 enter result dot v1 v2, and bam, just like that. And that's pretty cool. I think it is. I think it's okay. I think it's okay. Boink, 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 and boink, and add a couple of those, and change the reference vectors. Well, the source vectors for the linear interpolation. Okay, so right now I am interpolating colors. Woo! Hyperuni. Oops. And because we are pushing colors at the same time and rate as the positions, then we know it's already all in order and ready to work. You just have to expose it to the shader, and then it's gonna be glory. It's gonna do glory. Glory is gonna rain on our happy faces, but through the means of good old colored 3D heckin' Spherinder type deal, which am I hip with the kids enough already? Okay. Okay, current colors, and then push triangle is gonna use current colors just like that, and push them to the array, and then current colors we are gonna concatenate just like that to our array of things. Offset 1. Well, it's all the same, right? Vertices 3D.length times 4. That's the offset of everything, and just multiply it. Okay, temp GL bind buffer data, buffer data, buffer everything at once without the extra thing. If JLA position, if JLA normal, and then we need an extra one. Oopsies, not like that. Then we need JLA color. Sorry, GLA color. GLA color is 3 floats, false and offset times 2. Projection matrix, that doesn't change anything. Draw arrays, doesn't change anything. Okay, but then we need to declare an extra vertex attribute. Position normal color. color like that. Then copy that. Oops, there. A color is gonna be a color. Oops, not there. A color. I could just like fucking copy paste. Okay, a color. Okay. I think we're good. No, we have to change the shader to include the actual A color. It's not an uniform, it's a varying V color. Bam. Instead of that, it's V color. And the other thing, attribute a position a normal, so we don't do that. Attribute vec3 a color. Bam! Shit. Okay, point size is okay. And then we have a varying. We don't have a normal, do we? Yeah, we do. Yeah. It's the stupid normal calculated as render time. Varying vec4 v color. Oops. Okay, and then v color is a vec4 of a color 1. Sounds good. Sounds good. Let's see how it plays, if it does. Wow. First try compilation. Never mind. Oh yeah, vector 4 has no field lerp, of course. Unknown identifier theta step. Oh, did I leave a theta step somewhere? 88? Yeah, I did. That's fine. What else? Vector 3 has no field lerp. Well, I will have you know that in fact, I can make it have it. Bam. Class vector 3 extend. Alright, so this is the thing that Hax has. For those of you who don't know it, it's called static extension. Static extension. The point is that if you name a function, if you have a static public function, that you give it a name, and for first argument it takes something of a class and another thing of the same. Well, it doesn't have to be the same, but b and then t of float and returns vector 3. Then you can say, if you do like using vector 3 extend, then you can do like new vector 3 blah blah blah. Yeah, I'm just gonna do the simple way. And you can just do that. A.lerp bt. Although lerp is not defined, as you can see in the terminal, vector 3 has no field lerp, so I can just add a field lerp to vector 3, just like that. So it's pretty cool. It's called static extension, just like that. Bam. And I dig it. And what that's going to be is b.subtract a scale by t, oops, add a. Easy like that. That's a lerp right there. Well, actually, vector 4, do you have all of these things? Subtract, scale by, you have add, that's cool. Subtract and scale by, okay. Cool. So that should be it. And then in surrender, all we do is using vector 3 dot vector 3 extender. I think is how we do it. Module vector 3 does not define type vector 3 extender. Did I call it extend? I did. Extender, so I meant. Void has no field add. Yeah, I guess it doesn't. Void has no field add. What? Vector 3 dot hx 8. What? B dot. Oh, scale by doesn't return anything. Ah, it's not reentrant. See, this is why you do reentrants, because it's boring. It's annoying if you don't do it. Subtract a. Bam. I don't even know how reentrant or not reentrant everything is. So c dot subtract a. How reentrant are you? You don't say. Oh, it returns a new vector. Okay, so I'm assuming it's reentrant. B dot subtract A. C dot scale by T. Because then it doesn't return anything, does it? Scale by doesn't return anything, so it's in place. Scale by T, and then return C dot add A. Okay, this should do. Oops, my bad. My bad. Forgot how that worked. Int should be array of float. Oh, what's in it now? What is that now? Oh yeah, extra, of course. What is it? Colors? Did I name it? Colors 3D. Colors 3D. Add it everywhere. Yeah, because I have to tell the push triangle function where to push the colors, of course. There. That should do. That should do. It won't. Array vector 3 should be array float. 298. 298. Oh yeah, of course. Colors 3D. Top parameters are invariant. I know that. Whoa. Whoa. What the hell? What the hell? What is this? Oh yeah, okay. I think I know. Over 4. And then it's gonna tell me I want an int and not a float. Yeah, float should be it, of course. Yeah, because now the array is actually much bigger than the amount of triangles that we want to draw. I'm guessing it's that. Not even. Well, I'll be damned. What is this? What's going on? Okay, I'm gonna let it play while I search for what's going on in here, just so you guys can see that, because it's taking a while to pick up the OpenGL thing. So it is working, right? But then I have an extra thing that I'm not sure where it comes from. You can see that the sphere has wonky colors, just like we wanted. However, there's also that thing. Pretty obvious. That thing is going on in the background. I'm not sure what that is about. Okay, I do believe that vertices 3D, normals, and colors 3D are supposed to have exactly as many elements in them. So I'm not sure what that's about. What that is about. Wait a minute. Colors, push vertex colors. Okay, new array float every time. Alright. Did I fuck up the sphere then? But why wasn't that here before? I don't understand. std int offset, that's not gonna cut it. I'm sorry. Vertices, oops. What we mean is vertices 3d.length. We want to draw that many elements, basically. No. How many elements? Yeah, no. That's what we want to draw, isn't it? I think. Okay, let's try it. Maybe it's that over 3, in fact. But I doubt it. Okay, it doesn't seem to be doing it. Maybe that over 3 then. I know what I'm doing, guys, I swear. OpenGL is always very confusing as to what counts what. Okay, it was... No, it wasn't over 3. Like, that's doing some weird shit. Ugh. That's kind of weird. I mean, it's just the color that's weird, right? Like the thing in itself. The 3D model is complete and it's doing what it's supposed to do. But the color is weird. Maybe it's because the thing is double-sided. maybe. Okay, it's kind of weird and also not very pretty. But hey, it does look like it's doing something that it's supposed to do, but from this I get that I may be the one who fucked shit up. And yeah. Because see, those triangles do not look good. It mostly looks good, right? But then it doesn't, because some triangles are. It seems like some triangles are upside down. And to test that theory, I'm gonna ignore the V color, and so that it doesn't error out, I'm just gonna use. No, well, it doesn't matter. I'm just gonna do it in blue, red, blue, blue. Green. We never had green yet, so let's do green. Okay. Let's see. Okay, yeah, the triangles are fine, just that the colors aren't interpolated correctly, it seems like. Correctly? Ooh, correctly. Correctly, I meant. Okay. So the green is okay. Like, the green is fine. But there's something else going on. Okay, if I do leave the color, what does it tell me again? How does it look? Okay, it's weird. Like, some triangles look upside down. Or something. Oh, I know why. Quad reordering. It's the quad reordering. You should remember, I'm trying the intersection between a 3D space and a tetrahedron can be a triangle, a quad, or a tetrahedron. And the quad can be, because I don't check for any particular order of the vertices, the quad can be self-intersecting, in which case I have to swap both integers. I have to swap values. I have to swap two vertices. Sorry, I'm getting there. And I also need to swap the colors, just like that. Temp is current colors 2. I need to swap vertices 2 and 3, and that includes their color. Current colors 2 is current colors 3, and then current colors 3 is temp. And that should fix it. Problem solving, let's go. Yeah, I was saying, wait, the color seems inverted, but what could it be? Yeah, there it is. Look at this. Isn't that better? Okay, so we successfully extruded a 3D sphere, including color information, into a 4D sphere. How is that? How'd you like that? And we actually see that indeed those are two different spheres, because this sphere is black and this sphere is blue and has no black part. So that's how you know it's both ends of the cylinder, in fact. Like, it's as if you were watching, like here, this sphere is black and green, and this sphere is blue and purple and red. And because it's actually both ends of the sphere, it would be as if you were seeing like two circles that would be both ends of the cylinder, but it's spheres and both ends of the sphere. So with visualizations like that, you can work and understand how 4D looks and works. And that's why I think it's interesting. Alright, so in other news, we have successfully interpolated 3D values into 4D space and back into 3D space in such a way that it makes sense to have those in 4D, to have everything in 4D. So yeah, pretty cool. We have interpolated color values. I think it's pretty neat. It's pretty neat if you ask me. Yeah, basically the fact that there are two spheres with different colors, it's because one set of spheres uses the minus dooth vertices, and one set of spheres uses the plus dooth vertices. And as such, if I'm not mistaken, yeah, it's different ends of it, different ends of the cylinder. Which I think is pretty cool. Yeah, I'm happy with that. Okay. Alright, I think we're gonna stop here. I like to stop after every big achievement, because then I have time to clean up the code for the next stream, and yeah, and and basically try and plan out everything a little bit better than I did this every time I do to plan it better than the time before. Alright, so there we go. 4D cylinder next to, okay, wait, I'm gonna have a little nice family picture. Where's my box? Okay, I just need to go to main. Okay, I'm gonna have -3 and 1. I'm gonna have a nice family picture of the 4D cylinder, like 4D color interpolated vertices and the 4D box, and they cute, and the kind of 4D shapes you wanna see in your friendly neighborhood. Friendly 4-dimensional neighborhood, of course. Look at this go. Alright, so I'm gonna wrap it up. If anybody has any more questions, now is the time, while I quickly read my mail and leave you to this happy mess of 4D math going on in the background. Well, it's the front, it's the foreground for you, but you get it. Alright, so this is it. This is the pinnacle of 4D rendering up to this point. It's not really, like Mega Cooling goes much farther than that. Alright, yeah, that does it. I can remove the points also. Like the cylinder still writes to GL point size, which is obviously not needed anymore. Okay, also I'm gonna for those interested, this project, it's not called anything particular. I just called it OpenGL test, but I'm gonna put the source code, on GitHub for everybody to see, and I'm gonna have different releases per stream, basically. It's gonna start at this stream, of course, because I didn't do that for the previous ones. But I'm not gonna touch anything right now. I'm gonna push it as is on the new GitHub that I'm gonna create right after that. I'm gonna put it on the clip description. This is gonna go on VOD, and you'll be able to access it. And on the description, I'll put the link to the GitHub repo, so that you can take a look at everything. I believe it's properly commented. I do believe. Well, yeah, it's roughly commented, and all the math is commented. Is what matters. Is what matters most. All right, so that'll be it. That's gonna be it. Thanks for coming, everybody, and I hope you enjoyed this. I hope your brain didn't melt too much. I'm sure it did. And yeah, if you indeed liked what you saw, make sure to return. Catch you later. Bye. Yeah, I'm gonna change my schedule a little bit. Like Monday evening is not a very smart choice for me to stream, so I'm gonna move that to Saturday afternoon for Europe. Also, I have an American stream Thursday at 5 a.m. Europe time, GMT -1. Which is equivalent to 10 p.m. CST, if I'm not mistaken. So if you're more interested in that, there's that. The Monday stream is gonna go to Saturday, as I said. Probably afternoon stream, like 3 p.m. or something. It's gonna be much easier for me and for viewers as well. So yeah, take note of that if you're interested. And I will see you all later. Thanks for coming again, and catch you later. As our good friend BitSlime said. Bye bye!